Okay, and there we are. Then I'll share my slides. Hello, everybody. I hope you had a good break. We are now at the introduction to mock LCLS-II proposals, and we will then directly proceed in the same Zoom session with the LCLS-II instrument presentation and virtual tour. And I just want to present a few slides about the mock-up proposals, and then we'll open most of my time slot of 15 minutes to questions from you if you have any. So the mock-up proposals are supposed to be proposals for a possible experiment at one of the LCLS or LCLS-II instruments or at the UED instrument. Please submit them by the end of the week, Friday, June 19th, noon Pacific time. And the contents of these proposals is maximum 4 pages of write-up with figures, including as sections, scientific case, an experimental procedure, and a table of the experimental team and also their roles in the LCLS experiments. I hope all of you, or at least most of you, have seen that I actually included a call for mock-up proposals on the Canvas platform. You can see that in the announcement and download it. And in addition to the write-up, we would like to see also a maximum 5-minute video, kind of an elevator speech for your proposal from you. And you can do whatever you want on this video. There are not really restrictions, just feel free, let your creativity run free. And we will rate these proposals over the weekend by a committee of Pulse researchers and UXSS lecturers. And we will identify the three best submitted proposals. And each member of these proposal groups will get a book award for that. And the announcement of the winners will be on the last session of the summer school next Monday. Let me see. Yeah, so about the group work to write these proposals, you have been assigned to a proposal group with a dedicated mentor. These groups are also accessible via Canvas. You have your own group homepage there. And I sent around a while ago also a description of how to access them. You will be able to have your first meeting with your group mentor in the session directly after the LCLS Virtual Tour. The Zoom links for these meetings are posted on your mock-up proposal group homepages. You can, to generate your proposals, you can use many different resources. You're basically free to use anything. You can use the Canvas platform, which has these group homepages. It has discussion functions. It has also collaborative writing functions. But you might also wanna talk some more in person via Zoom or Google Hangouts and share documents, for example, via Google Drive, but whatever works for you. If you feel like you have 2 or several good ideas within your group and want to pursue several ideas, you can also form subgroups within your group and then submit separate proposals. And that's basically what I just wanted to say in advance. And now I would like to open this discussion for questions. Are there any?
There was a question that said, is anyone going to carry a camera and run around LCLS for the virtual tour? I said yes.
Okay.
And then there was a question about what kind of video, and my answer was live. I'm not sure if this is what they were meaning by what kind of video, but
I think they were probably referring to this 5-minute video, which we want to see submitted in combination with the proposal.
I see. Okay.
And the answer is you can send me anything. This is really free to you. You can talk for 5 minutes about your proposal. You can make, if you want, an animation or whatever. And you the format you can send me this video in can be an upload to YouTube, or can be, let's say, an MP4 file, or whatever is accessible to you.
One more question. Can you submit a proposal as an individual?
You can in principle, but I wouldn't encourage it. I think it's really it's really supposed to be group work, and I think you can. If you write your own proposal, you might miss out a little bit on the group learning experience.
Next question, has the book award been determined yet?
Yes, it has been, but I will tell you in the end. It's gonna be an UXSS related book award.
Question, what is the suggested font size for the draft?
Let's say 11 points, but just be reasonable. It can be 12 if you feel like, but it shouldn't be 8.
Any other questions? We have been assigned to the group according to what?
According to your choice at the registration. If you didn't register with any choice and you feel like you are in the wrong proposal topic, please write me an email.
Question, is the idea that we are submitting a mock proposal for run 19 or runs in the future with full high rep rate operation as well?
The idea is that you submit a proposal for the time when we have high repetition rate soft X-ray FEL radiation, and high photon energy hard X-ray radiation, but still at the 120 Hertz repetition rate we have at the moment. So basically the status we will have after the LCLS-II upgrade. Okay. If there are not more questions, I will give a brief introduction to this following LCLS tour.
Sorry, is there any template for the mock proposal?
There is not. Are my slides visible again?
Yes.
Okay. I will hope that I can actually switch to the next one. Okay, yeah, so I just kind of wanted to show you what the schedule for this virtual tour is going to be like. So David Fritz will first give us a 15-minute overview over the LCLS facility, where we are coming from, basically, and what is planned for the future. And then we will go to individual instrument presentations, and we will start at the LCLS Near Hall. You see that now here with a yellow sign here on the map, and we will have 4 Hutch presentations there. And the Hutch presentations are supposed to go the following way. The Beamline scientist presenting will present about 10 minutes worth of slides about the science case and the specifics of the Hutch. And then we will switch to Mike Miniti, who is actually on site today, and he will provide live video streaming from the Hutch, and then the respective Beamline scientist can explain a little bit more what is actually there in terms of hardware in the Hutch. So we will first do 4 Hutches in the near experimental hall. Then we will virtually go through the large X-ray transport tunnel in between the near and the far experimental hall and see 4 more Hutch presentations. Those are all hard X-ray Hutches. And in the end, we will also see a 15-minute presentation about the capabilities of the UAD facility. And that is basically the end of my introduction here. And I would like to hand over to David Fritz. We are a little bit early in time, but I think this is actually very good and not really a problem.
Great, thank you, Thomas. Can everyone hear me?
I think so.
Okay, excellent. So yeah, just going to give a quick introduction to the LCLS complex, which recently we've been doing a lot of installations for LCLS-II, so I will talk a bit on both. But before, I just wanted to thank the organizers for the opportunity to speak to you. Also wanted to acknowledge our funding agency, which is the U.S. Department of Energy, Office of Science, and as well the LCLS and LCLS-II teams and associated partner laboratories shown here. So just to begin with, and a quick introduction to SLAC. So early in the 1960s, the construction of so-called Project M, which was this big electron accelerator, was done to primarily enable particle physics experiments. And this long, 3-kilometer long electron accelerator was capable of accelerating electrons up to 50 GeV and with 120 Hertz repetition rate. And what's not kind of visible from this above ground picture is sort of all of the various experiments and rings and tunnels that were constructed for doing these particle physics experiments. So initially, there's this, well, you can look at the schematic on the right to see all the different types of experiments that were conducted. And at SLAC, I would say roughly every 10 to 15 years, a new experiment was thought of, and that would initiate a new construction project. So there's actually, this initial experiments were done in the so-called fixed target end stations, end station A and end station B. And then the next phase was the Stanford Linear Collider, which was these 2 rings that would collide electrons and positrons. And then following that was sort of the PEP rings, which were recirculating rings and storage rings. And so every 10 to 15 years, SLAC would embark on a major new construction project. And about 10 years ago, we started working on LCLS, and the SLAC slate was chosen because a high brightness, high energy electron accelerator is one of the main ingredients to creating an X-ray FEL. So by basically reusing the SLAC infrastructure, that gave the potential of really accelerating the timeline of realizing an X-ray laser. And so that proposal was initially conceived by Claudio Pellegrini, and with the help of Herman Winnick back in 1992, was sort of a workshop was held, 28 years ago to propose using the SLAC accelerator to create a short wavelength FEL. And and soon after that, not soon after that, but I think I did the math wrong. I have to update the slide, but 20 some years after that, in 2009, the LCLS was realized. And so the LCLS only used a 15 GeV electron energy, and so there's just the last 1 kilometer of the SLAC accelerator was used to then feed beam into a fixed gap undulator, which is a small picture shown here on the left. That's where these ultra-fast X-ray pulses are created, and the beam is then distributed down to 2 experiment halls, a near hall and a far hall. And here's just a few images of some of the instruments that you will see on the virtual tour coming up. Now, recently, SLAC has embarked on the so-called LCLS-II project, where the first kilometer of accelerator is being replaced with a modern superconducting accelerator. And so this table just shows a side-by-side comparison of the existing accelerator modules with LCLS-I and the superconducting modules with LCLS-II on the right. So just kind of a comparison. The gradient, which is basically how much energy can be given to the electron beam per meter of this so-called warm structure, is around 25 megavolts per meter, whereas that's a little bit lower for the superconducting accelerators or superconducting cavities. The electron energy of 1 kilometer of the LCLS-I system can reach this 15 GeV energy, whereas this initial installation with LCLS-II, we're populating about 700 meters of the first kilometer with superconducting modules, and the target electron energy is 4 GeV. Now, the main difference between, the main advantage of moving to a superconducting system is that once these cavities are energized with a microwave pulse, they stay energized for a very long time. They have a very high Q, sort of 1,000,000 times higher than these sort of conventional conducting cavities. And so, whereas with those cavities, when they're energized, they stay energized for about a microsecond. If we run in some special operating modes, we can actually stuff in, 2, 4, or 8 bunches within this pulse. But 95% of the time, we are operating with just single bunches. Whereas with the superconducting machine, basically it's on continuously, it's on all the time. And so that allows us to have a bunch repetition rate approaching a megahertz. So this is an enormous jump in capability for us. It'll be truly a new world when we start up. And here's just the schematic overview of the accelerator, where you have these this new superconducting accelerator in the first section of the LINAC. followed by a bypass line, and then there's the existing copper accelerator. So LCLS is kind of a unique facility where we have two totally independent electron accelerators that we can use to feed two new undulators that have been recently installed in the undulator hall. The table on the bottom shows some parameters for LCLS, and so currently, we still haven't started up yet, but this was before we shut down earlier in the year. We were able to laze down to the carbon edge around 250 eV, up to the selenium K edge around 12.8 keV. With the copper accelerator, we have a pulse repetition rate of 120 hertz, and we routinely could achieve about a 4 millijoule per pulse energy, and that translates into about 10 to the 14 photons per second. Now, now that we've replaced our hard X-ray undulator, the period was changed, and this has allowed us to extend the photon energy reach from 12 keV up to 25 keV, while maintaining most of the other parameters. Now, of course, the big change is when we this column in the middle shows what we anticipate happening when we feed the long period soft X-ray undulator with this 10 GeV copper energy beam. And the big change there is that we anticipate being able to make very large pulses up to 10 or 8 or 10 millijoules per pulse produced out of that configuration. Now, once we feed the superconducting accelerator into these undulators, we expect on the hard X-ray line, the photon energy reach will be about 1 to 5 keV, where on the soft X-ray line it'll be about 250 to EV to 1.6 keV. Again, with a very high pulse repetition rate. The per pulse energy is a bit lower than what we can realize with the copper accelerator, but with the repetition rate is so much higher that our average number of photons per second is many orders of magnitude higher than what could be realized before. So this is just an image of the current undulator hall, where we have the soft X-ray variable gap undulator on the left and the hard X-ray variable gap undulator on the right. The two look a little different is because the polarization of the hard X-ray line produces a vertically polarized beam, whereas the soft X-ray line produces a horizontally polarized beam. This is the instrument layout. We have a couple of instruments that are currently in construction in the near hall, but as Thomas mentioned, we have sort of three instruments that are being new instruments that are being installed to use the higher repetition rate machine. The near hall is mostly dedicated for sort of soft X-ray experiments, and as well as tender X-ray experiments in the TXI instrument. And we have 5 hard X-ray instruments that are one in the near hall and 4 in the far hall. And with that, I will pause and take any questions that anyone may have.
Awesome. Thank you so much for this really comprehensive overview. We already have one question, and that is, what are the primary mechanical differences between the hard and soft X-ray undulators?
Yeah, I mean, without going into too many details, the soft X-ray undulator that has the magnetic arrays and jaws that open vertically, and that's sort of traditionally the mechanical configuration that is seen on storage ring facilities. The hard X-ray undulator has mechanical jaws that actually open horizontally. And so that's the reason why the two polarizations are orthogonal to each other.
Great, thanks. And then there's another question. What are the pulse durations of hard and soft X-rays?
So the short answer is it depends on the configuration of the machine. The bunch charge can be varied to produce shorter or longer pulses on the accelerator, and also what accelerator is used. For the copper machine, I think we routinely achieve 20, 30 femtosecond pulse durations in sort of normal operating conditions. On the superconducting machine, with a relatively nominal pulse duration, would be somewhere on the order of 50 to 100 femtoseconds, but there are special operating modes that can be implemented to effectively cause only a fraction of the bunch to laze. And so in those operating modes, very short pulses can be realized. We've demonstrated sub 1 femtosecond pulses running in some of these special modes before. So fortunately, it's not a straightforward answer. It really depends on the configuration of the machine.
Thank you. Then the next question is it possible to do X-ray photon correlation spectroscopy with soft X-rays?
Yes, we are. I mean, essentially, that requires an X-ray area detector, and we're investing in. We're developing these systems now. At the moment, those are unlikely to, the system we're currently developing is unlikely to work at a repetition rate greater than, 10 to 25 kilohertz. But there are ideas to basically build specialized detectors for XPCS that potentially could work at much higher repetition rates.
Okay, and then another question, will the diagnostics also work in high repetition rates such as 900,000 hertz?
Yes, I think most of the diagnostics are designed to work at those repetition rates. There are some that may not work quite up to that rate, but certainly most can work at a 100 kilohertz repetition rate.
Okay, great. What is the expected timing jitter for soft and hard X-ray pulses?
So we expect, I mean, with the copper accelerator, we anticipate having a similar temporal jitter than that we've always had, which is on the order of a few hundred femtoseconds. We expect this to improve drastically with the superconducting machine, where the energy stability and various other parameters of the machine, we can implement high frequency feedback loops to control these parameters in a much better way than we can with the copper accelerator. And so, we're anticipating a jitter that's sort of, sub 50 femtoseconds. And I know that has been exceeded at, the European XFEL, and we're anticipating that we're hoping that we can exceed that as well. Perfect.
There are quite a bit more questions. You have a very responsive audience here, but I think because of the time, I have to finish this discussion now. I want to thank you again very much for this overview.
You're welcome, and I will during the other presentations, I will type in answers to these
awesome
questions.
Yes, that's great. That's great. Awesome. Thank you very much. And then we will go to the first Hutch presentation that's going to be given by Giacomo Koslovic.
Can you hear me?
Yes.
Thank you, everybody. So I'll start by giving a bit of an overview on the NEH and how the NEH 2.2 Hutch, which is also called a RIX, is situated. Sorry, let me go to full screen. That's better. There you go. So I'm Giacomo Kozlovic. I'm one of the scientists of the RIX team working in the NEH 2.2. I'm a laser scientist, so actually, if you have a question more on the laser side, I will probably have more answers, and I will try, of course, to answer all the questions about the X-ray side as well, because I do experiments as user as well, and I'm involved in all the experiments in RIX. So a couple of big points to highlight on the RIX Hutch is that, so we're covering the soft X-ray energy range from 250 eV to 1.6 kV. So it's a little bit limited in respect to the range, for example, you can get down in the TMO Hutch or the TXI Hutch. But that's actually to really improve the quality of the experiments that we can do in the soft X-ray in this regime. And it's one of the only Hutch here that has a monochromator. It's the only one that has a monochromator for the soft X-ray. So that's very important and allows us to do some experiments that can only be done in this Hutch. Specifically, resonant inelastic X-ray scattering is primarily done here at LCLS. So we have two end stations in this Hutch. One is ChemRix, where we can focus a little bit more on liquids and in terms of sample environment. And we have QRix, which instead focus on solid. Here is a side view of the NEH. Actually, sorry, going back 1 second, I wanted to point out that we are right nearby the laser hall. So this is where all the high repetition rate lasers will be situated to deliver a laser down to each Hutch. And so we have actually a raised floor here where we deliver the laser to each end station, while the X-ray are delivered through a tube that goes through the first floor here. And here you can see from the front end enclosure, which is where there is actually the electron beam dump and where the X-rays are delivered to the various Hutches, we have a beam pipe that delivers the beam up to the second floor. So it goes through the ceiling in this case, and here we have the mono very conveniently located at the ceiling of Hutch 1.1. Of course, that's a joke that is convenient, but of course, that's the best location that we have for mono operations in 2.2. And so then we have the various beam diagnostics for the beam delivering up in the Hutch upstairs, and then we have the two end stations. So what kind of science are we targeting? So first of all, we have two end stations, as I said, so they target two different science cases. This is actually not a full description of all the science cases that we can tackle. These are just two focus in terms of science targets. So we have the ChemRix that can tackle the problems in condensed phase chemistry and photocatalysis. We can study systems, for example, involved in photosynthesis and catalysis that is triggered by a laser pulse, for example. And with QRix instead, we'll focus on the understanding and controlling of quantum materials. And so in both of these cases, the most common experiment that we'll do is one where we have a light excitation that can be a laser pulse, for example, and we'll study, we'll follow the system doing ultrafast screenshots of the evolution of the system. So how do we do these screenshots? So we do several type of techniques in the RIX Hutch. So I will not cover all of them comprehensively. We do X-ray absorption, we do X-ray emission, we do resonant elastic X-ray scattering, we do X-ray photon correlation spectroscopy. All these techniques can be covered, but one of the primary focus of the Hutch is really RIX, so resonant inelastic X-ray scattering. So the RIX technique is it's a technique in which you have a photon in and a photon out. So you gain information on the system by studying the energy and momentum of the photon emitted by the sample. And of course, by tuning the incoming photon to specific resonances. So the idea is that you can have an excitation of a core level, from a core level up to the Fermi level and close to the valence band. So you can gain information about the valence electrons, which are very important in condensed matter physics and in chemistry. Those are the electrons that determine your transport property if you study a material, or your coordination physics in chemistry. So there are some unique possibilities for doing this kind of experiments at LCLS. First of all, this is the only opportunity to do time resolve RICs, so ultra fast time resolution for these kind of experiments. And we can go down to the Fourier transform limit in this case. And then, of course, this technique is photon hungry. I don't have right here an estimation of how few photons we get, but whenever we tried, for example, with LCLS-I, we got 1 photon per shot at the spectrometer, for example. So it is very challenging to do these experiments and obtain good signal to noise. So there is a big opportunity going to LCLS-II, where we'll have the high repetition rate machine to really get a lot of photons to study this science case. So here there is an interesting comparison on how LCLS-II will compare to other beamlines where people do RICs, for example. So we expect to have a couple of orders of magnitude gain in respect of what one can do now. So this is one important aspect as well. Our resolution RICs is possible with this, with LCLS-II. So going back to the science case on liquids, for example, we can do RICs in liquids and obtain maps, for example, as a function of the incident photon energy and the outcoming energy. And so this allows us to probe the occupied and unoccupied molecular orbitals. We can study photocatalytic systems and electrochemical reactions in relevant systems. And we can study charge transfer in 3D transition metal complexes. So this is kind of the overview on the photocatalysis and coordination chemistry. In terms of solid state samples, which is the focus of QRICs instead, we can study emergent properties in materials. So with the high resolution RICs, for example, we can study different type of excitations and collective modes in materials, such as phonons and bimagnons or magnons. So this is really something that can be opened up by the ability of doing high resolution RICs, so something below 50 millieV in terms of resolution. And then we have been doing already with LCLS-I some experiments of ultrafast RICs with a little bit coarser energy resolution. And here, of course, we can bring in ultrafast excitation with a laser pulse, which can be coherent or selective excitations of specific vibrational modes. We can do sudden quench or creation of quantum orders. And so this is an interesting example of one experiment that was done with the spectrometer that is now getting installed in ChemRICs, which doesn't have the high resolution, but it allows you to study the dynamics with about 400 millieV resolution. And so the idea here is to go toward the control and understanding of emergent properties of quantum materials. So in terms of the key beamline performances are listed over here. I hope this can be helpful also for the mock-up proposal. In terms of energy range, I listed here some of the elements and the edges that you can cover with this beamline. So we have K edges in carbon, nitrogen, and oxygen. We have L edges in transition metal oxides, as well as some M edges. And then there is upcoming an extension to 1.6 keV, which will allow also some M edges on the rare earth materials. Another important aspect is the bandwidth control. We're able to both determine the incoming monochromatic beam and as well as the resolution that we can get on the spectrometer. So for the ChemRICs, the target goal is really to have about something between 1,000 and 5,000 resolving power. So about 200 millieV in terms of resolution. It's important to keep in mind that there is always a balance between how much energy resolution you want and how much time resolution you want. So we always have to work within the Fourier limit at maximum. And so for the case of the QRICs, The ultimate goal is to be able to go up to 50,000 resolving power. So that will allow us to go below 50 millieV in terms of energy resolution. Here's some other details that can be interested. I will not go through all of them. The laser delivery is also different. We focus more in the UV and visible range for ChemRix, while for QRix, the focus is more on the mid-infrared and terahertz. And we are aiming to be able to get to a synchronization timescales better than 10 femtoseconds in terms of synchronization between X-ray and laser driving pulses. Then, of course, what is the actual time resolution will depend on the X-ray pulse duration and the laser pulse duration. So it's more involved. So just here a layout of the beamline, how it will look ultimately for LCLS-II. So we have several beam diagnostics. We have a laser table where we deliver the optical laser to the first end station, which is QRix, which has the big arm that is about a 6-meter arm that allows to get the high resolution RIX spectrum. And then we have ChemRix over here with the portable VLS spectrometer, which is one that we're already been using at LCLS. And this will instead will have the capability to make liquid sheet and liquid jet in the chamber. So this is where I will probably transition to the tour part. If we have Mike ready, this is more an overview of the whole hutch. So I don't know, where is he right now?
Perfect. Can you stop sharing your slide?
Okay.
And then Mike is on the call here. Yes. And
So unfortunately, we're having a little bit of a technical difficulty with our little mount. And so I've got to hold it to you. We'll sort it out here for now. Can't really explain why, but so what we're looking at here now, and unfortunately I can't really go too much into this hutch because, as David and Giacomo said, we are in a construction process here within the hutch itself. And so what we're looking at here is exactly where the big 6-meter QX arm would be, where you see this large area swept out in front of us. And here you can kind of see everyone hard at work, getting the next and biggest and best, greatest thing up and running. So are there any questions? I'm not sure. There's really much more I can't go in because I don't have all my PPE donned.
Okay, great. I mean, NEH 2.2 is, as you can all see, still a construction site, so there is probably also not too much to see. Maybe instead, with the remaining time of 2 minutes, I can ask some of the questions, and there are a lot of questions here live to Giacomo.
Yeah.
So one question is, and that's actually an upvoted question, so it seems to be an important one, how the liquid cell is performed. How is it constructed?
So we have a liquid jet, basically. In some cases, also a liquid sheet, in the sense that is a very thin jet that we can make. There is a sample delivery environment that is taken care of at LCLS and is designed for the end station. For specific question on the liquid jet, I would probably defer to Jay Korolek, who was one of the sample delivery expert in RIX. So there will be a dedicated liquid sheet for the end station in ChemRix.
Thank you. And then there's a further question. Can we do RIX that is XANES with hard X-rays?
Well, this will have to be on a different end station. We cannot do hard X-rays in RIX.
Okay. And maybe a last question. Is there any thickness limitation in your RIX experiment station for solid samples?
Well, not really. Depends if you're doing an experiment in transmission or in scattering, in reflection, let's say. So if you're doing in transmission, of course, you want the sample to be thin enough so that you have enough photon flux going through. But in most of the cases, we will do the experiment in reflection geometry, so scattering backward out of the surface. So in that case, you don't have any concern with the thickness.
Perfect. Thank you so much, Giacomo. This was a really great overview. If you could stay on maybe a few more minutes and answer the rest of the question on the chat, because there's a lot going on.
No problem.
And I'm gonna switch over now to Peter Walter, who will tell you something about TMO, our AMO hutch. Peter, are you muted?
Okay, let me
Here we
start
are.
also my, wait a second, 1 second, sorry. Also, so here I am, and now share my screen. So, first question, can everyone see my presentation?
Yes, we can.
Okay, and the mouse pointer?
Yes, I see a mouse pointer. Yes, it's moving.
Okay.
Yes.
Okay, great. So yeah, thanks for giving me the chance to talk to you and present our time-resolved atomic and molecular optics end station, TMO at LCLS. And as David mentioned, we have the luxury situation that we have actually two accelerators. The warm or copper accelerator, LCLS, with 120 Hertz, and LCLS-II, our superconducting nearly 1 megahertz machine. And TMO can take the beam from both accelerators, actually, because of this nice switch out that we have right before the undulators, which brings us in a great situation that we can use the high peak power from the copper accelerator for, as David says, higher than 8 millijoules peak power for our experiments in TMO. The disadvantage is the rather lower rep rate, as mentioned, and we don't have a deturper, so we have rather long pulses or absolutely short pulses due to our X-leap capabilities, which is our compress scheme with wigglers, our electron bunches to get sub-femtosecond pulses. And LCLS can also take the full high rep rate from, TMO can also take the full high rep rate from LCLS-II, which is really nice. And if you see here, compared to European XFEL, we will have about 1 microsecond bunch as separation, and not this train structure as the European XFEL has it, which is for charged particle spectroscopy, a more suitable situation. So for TMO has two focus spots where we can perform different charged particle spectroscopy experiments, and we can then take the full advantage of LCLS-II with the megahertz, with short pulses, and especially for our coincidence experiment end station DREAM, which I will talk about a little later. So in our hutch TMO, this is our end station. The undulators, the variable gap undulators behind this wall, the beam is coming in from here. We have our KB system, which focus down the beam into our IP1. And then we have a granite for a bunch of diagnostics and a wavefront sensor. And then we have our second KB system. So we refocus the beam into our second IP, our reaction microscope. And then we have also a bunch of diagnostics behind that. And what you can see here behind that beamline is our laser mods table, where we get the laser from our laser lab upstairs, and then we can optimize the laser for our IPs. And we have two of these tables, so both IPs can be operated completely independent from each other. And the scientific motivation for TMO is we want to investigate charge migration and charge transfer in its natural time scale. And therefore you need rather short pulses to invest, especially charge migration and charge transfer in its natural time scale. And oh, this video is not working. So what does it mean is in nature, every photon introduced process starts with charge migration, and that's what we eventually want to investigate with TMO. And that's the motivation that I will talk about a little more and later in the slides. And for now, I want to talk about our IP1, our next generation atomic, molecular, and accelerator science and technology experiments focus spot, IP1. So to optimize this end station, we had the idea of variable standardized end station that we move in and out to limit the amount of time that we have to to do by setting up the experiment at the focus spot. And for IP1, we have several end stations now. We have our LAMP end station, which has a double-sided VMI, where you have on the short side an electron side, and then along the ion side, where you can do charge particle spectroscopy for ions and electrons in covariance and also in coincidence, which is a nice tool for strong field physics or electron covariance or coincidence. And by taking the yield of the charged particles, you also could do some X-ray absorption spectroscopy. Another end station that we have is our coaxial or CVMI, which we have used for streaking experiments. When streaking is when you have a linear X-ray pulse coming in, ionize your sample gas, and then you have a circular polarized 800 nanometer or IR pulse where the vector potential of the circular polarized laser then streaks your electrons, and by that you get information also on the pulse structure on your SARS pulse or the pulse duration. And the third end station that's currently in the making is our 16 our high resolution electron instrument, our new version of the DAISY cookie box, where you have 16 time-of-flight TOFs arranged around the interaction region, and these electron time-of-flight spectrometers are supposed to have a huge window of 60 electron volts with a resolution of better than a quarter EV, and an acceptance angle of 1 and later of 5 degree. So to increase the electron efficiency by increasing the acceptance angle. And for the retardation of our electrons, we want to go up to 2000 volts to do a spectroscopy also on several edges. And by having 16 independent TOFs, you can think about alternative or independent retardation settings. So you can either have an interleaving AB retardation settings and look for two site-specific edges in your sample, or you can make them completely independent and have a really huge window. And because it's an MCP based, it works for a megahertz repetition rate. And it's also a nice polarization diagnostic, or because of the streaking, you can get the whole SARS profile and the pulse duration And it also gives you then, because of electron spectroscopy, of course, relative intensity and energy. And for IP2, we have our dynamic reaction microscope DREAM, which is our cold TRIMS end station. Apparently, none of my videos are working. I don't know why. So cold TRIMS is a really nice charged particle spectroscopy instrument where you can detect ions and electrons in coincidence. And the nice thing is you try to have one photon interact with one atom or molecule, and then by getting the time of flight and the position on your detectors, you get the full momentum of your molecule. And then if you do pump and probe, you can have the whole reaction of a pump and probe experiment time resolved, and that's why people also call it a reaction microscope. And DREAM, other than IP1, is a fixed end station. This will not be changed, and we have our 4-stage skimmer. We have a closed laser in-coupling and out-coupling. We have a spectrometer inside our main chamber. We have Helmholtz coils for our magnetic field. And here you can see inside where the X-rays is coming from the left, and the laser is coming from here, get bounced off our focusing mirror, get bounced out over here. You see here is the field of view for a microscope, sample paddle, and the spectrometer. Everything is really close, which makes it a really, really challenging end station, especially if you want to go to 10 to minus 11 millibar in pressure. And so these are the two end stations that we have. And the long-term key requirement is to have a focus spot smaller than a micron. And of course, because our mirrors are bendable, we can variate our focus from 10 to from one smaller than 1 micron to more than 50 microns. We want to have high repetition rate because we do charged particle spectroscopy, and especially if you want to go coincidences, you need more than 100 kilohertz. We want to have sub-femtosecond X-ray pulses to follow all nature events in their inherent time scale. And we want to do through zero delays to start your time delays actually with 0 femtoseconds and then go from there. We need high intensity pulses for to perform high field physics. That we can do. We need an energy range where we have a lot of site-specific edges. Starts at the carbon edge and goes above silicon and aluminum. And we're also going to have a so-called delta undulator, which gives us circular polarized X-rays. On the detector requirement, of course, we need high resolution electron and ion detectors. We need large time of flight windows. And for most of our experimental setups, we need position and time resolution, which will be delay lines in first place and later a specialized pixel or a pixelated detector. And of course, we need to do gas phase angular resolved photoelectron spectroscopy. And the diagnostic, of course, needs to be capable of diagnose attosecond pulses, and our diagnostic also needs a wavefront sensor to get the perfect focus spot. And if you do pump and probe experiment, the timing jitter needs to be, of course, as small or as little as possible. And with these slides and the main capabilities of TMO, I would like then to end this presentation and go to questions or to Mike inside the TMO hutch.
Thank you, Peter, very much for this overview. Mike, are you? Can you stop sharing your slide, Peter?
Yeah,
And
I'm here.
And there is Mike. So,
oh yeah, construction. Oh.
It's definitely a construction zone still here, that's for sure.
In this
you're-
tiny, in this tiny yellow square that is behind this crane, that's where the wall is, that's where the beam comes out. And this is what you see here, this granite, this gap in this granite is the gap for our KB system. And then on this steel plates that you see here, there is an laser in coupling, laser out, and the diagnostic pedal, and Mike is staying literally where IP1 is. So the focus, he was staying there. This is the gap we have left to move in and out our end stations. So granite on the left, and then granite on the right is the granite on the left is the diagnostic granite, where we have our laser out coupling, the laser time tool, the wavefront sensor. And then behind that you see no gap between the two granites, because then there is the KB tank for Dream that will be installed there. And then you see the next, the granite right there that starts on, ends on the right this is the gap that you see there in this granite on the right is for the catcher of the Dream station. And this is the plateau for the Dream end station. And then there's again, the steel plates for all these diagnostics. And then if you move to the right, pan out to the right, then there's the photon dump. This is then the end of TMO. So and we have to fill this whole hutch until the mid of August. So there's a lot of work for us. Thank you.
Cool. Thank you very much. I think in the interest of time, we have to go on. It would be great, Peter, if you would stay a little bit on for a little bit longer, because there are a lot of questions in the Q&A.
Okay, thank you.
Thank you. And here comes Andy Aquila with his presentation of the Tender X-ray instrument. Andy,
can you see my slides?
The stage is yours. Yes.
Okay, great. And I hope everyone can hear me. So thank you for letting me tell you about what I personally think is the coolest instrument, the Tender X-ray instrument. I'll explain why I think it's the most interesting of the new instruments, if not all the instruments. So first off, I think there was a question in the Q&A of what exactly do we define as tender? And I personally defined it, it's kind of not a consistently defined from facility to facility, but I define it from the silicon K edge to the iron K edge. Most synchrotrons have only one or two instruments dedicated to this energy range. They do a lot of ambient pressure photoemission, X-ray fluorescence, nanoprobing. The reason for this is it has some benefits of hard X-rays and some benefits of the soft X-rays, but it's very hard to make X-ray optics for. So most experiments can be in low vacuum, which is better than soft X-rays, but you can do a lot of experiments at ambient air pressure with hard X-rays. It has better penetration in the materials than soft X-rays, which do a lot of surface science. But as I said, that comes with some costs. So when you want to do diffraction experiments, you don't get down to the angstrom level. You really can get maybe at most 3 angstroms, but you have better scattering. So this is where there's a lot of interesting science. The sulfur, the phosphor edges have K edges in these energy ranges. So there's a lot of cool elements and elements of specificity which we can provide. So a simplified layout of the TXI instrument, and one of the reasons I think it's the coolest is we can take X-rays from both undulators. And let me iterate this again. We can take X-rays from both undulators simultaneously. And I just realized this picture is not quite right. The soft X-ray, the hard X-ray has a different polarization. This is definitely an old slide. Our focal spot size is going to be about 1 micron to 10 microns. We have bendable KBs. We are really focusing on liquid jets and aerosols, but we also can do fixed targets and cryo temperatures. I'll explain why we want to focus on those. This will be the, of the new instruments, this will be the first with a high repetition rate detector, hopefully operating about 5 to 10 kilohertz initially and going up to maybe 20, 25. And that will be an Slack developed EPIX 10K. So it means it can actually collect up to 10,000 photons per pixel. and has variable gain, so you can actually we can actually see individual photons, or count individual photons. On the soft X-ray side, the mirrors were designed to go from 200 eV to 5 kV, and the hard X-ray side, we go up to from 1 to 7 kV, with possibilities of hitting a few photon energies up to 10, maybe a little higher kV photon energies. The two beams cross at about 95 milliradians, which is about 5.4 degrees. So they're not coming collinearly, which has some really interesting benefits. And we can do a lot of unique experiments this way. You just can't get them collinearly just based on the fact that the undulators are separated by about 2.5 meters, and overlapping the two beams collinearly would be very challenging from an X-ray optics point of view. We do support a lot of spectrometers, but let me reiterate. The most important thing is this is the only instrument in the world that actually can cross two X-ray beams, two FEL beams, in fact. I think there's SOCLA, they have a synchrotron FEL overlap, but this is the one that we can actually do some really cool science. Now, if you think about lasers, visible light lasers, once we started getting into the nonlinear regime and actually being able to change frequencies and use do pump probe, that's when things started. We started doing a lot more spectroscopy. So this is where I want to take TXI. This is a kind of a long table, but there's a global requirements document out, and pretty much we want to do these nonlinear spectroscopies, coincident catholysis, look at phonon dynamics, look at other fluctuations, and the gist of it is TXI is dedicated towards X-ray pump, X-ray probe in all forms, and also forward scattering at high repetition rates for biological imaging. These two seem very complementary, and they both really utilize the tender X-ray regime very well. So the requirements for the experiments and the instrument, on the soft X-ray side, we can go from about, I said, a couple hundred eV up to 5 kV with complete harmonic rejection between 1.25 kV and 5 kV. On the soft X-ray side, we can do harmonic rejection from 1.75 kV to 7 kV, maybe pushing up to 8 if we really wanted to, but at lower repetition rates. And we can go from 1 to probably 10 if we adjust the mirrors a little bit, or coatings. The mirrors are coated with boron carbide and nickel. Actually, to be honest, the nickel has a slight thin boron carbide coating on top of it for specific reasons of keeping the mirrors, we can clean them. The mirrors can hold up to 200 watts of power. And I said we were looking for a spot size about 1 to 10 microns and a beam position stability about better than 10% of the full path max, so 100 nanometers. And we can probably synchronize, we're hoping to synchronize the FEL to within 10 femtoseconds. And that's going to be challenging, if not, if you think about a 3 kilometer long facility, this is effectively at speed of light, that's 3 microns over 3 kilometers. So what's a hutch layout look like? This is the hutch layout. So far, we have KBs in the front. We have a diagnostic stand in the back, which has actually a wavefront sensor, power monitors for each of the two beams. And then the end station will go here. We're still in the process of designing the end station. TXI is a third of the new instruments to come online, and it'll be coming online in 2023. So we're still in the process of doing the design. We had a little more time than the other instruments. So the mirrors are actually very complicated. We've actually swapped the order of the KBs to actually get the mirrors closer to the end station, which makes us have a smaller spot. They have to be bendable, because if you're going to overlap 2 spots in space, when you're using a KB system, Kirkpatrick-Baez mirrors, they're pretty much elliptically polished mirrors, or you can think of them as cylinders. As you change the angle to overlap those 2 spots, you actually change where the focal position is. So to compensate with that, you actually have to bend your mirrors. So a lot of thought went into actually getting this system working, looking at the mirror efficiencies, what coatings to use on the soft and hard X-rays, where we can cut out harmonics, which mirrors to use, boron carbide versus nickel. We even looked at other materials. Turns out at these high repetition rates and high fluences, we can actually start melting materials. So we have to be very cautious of what we use and choose. We wanted a 1 micron spot, mostly because if we're doing nonlinear physics, you want to pack as many photons into a small spot as possible, which really determined, based on the spot's source point, really determined how far away the mirrors have to be, which means the second mirror has to be 2 meters away from the interaction point. It also tells us what our Rayleigh range is, because these are lasers after all. And we can actually do some very back of the envelope calculations when it comes to diffraction limit. It's optics. Based on the length of the optics, we chose 1 meter mirrors to get us diffraction limited and collect force sigma of the beam. These are probably all more information than you want to know to design your experiment, but I want to say in all these instruments, a lot of detail went into planning how these, all the hardware and software setups you were going to utilize, even down to the nitty gritty of what materials to use. Overlapping 2 X-ray pulses is challenging. We could do it, we were initially going to do it with copper and hard, and we'll probably still do that. But the jitter is going to be about 100 femtoseconds after just doing the quick calculation. So the easier way to do it is to double pump our the photocathode of the superconducting accelerator. Now, as David mentioned, they have a huge Q or large quality factor, so they actually resonate for a long time. So if we double pump with separation that's of the beat of 5.4 nanoseconds, we can use a electromagnetic fast kicker at high repetition rate, which is effectively dumping a huge amount of charge onto 2 plates in a vacuum chamber to move the electron beam over. Actually, it's more complicated than that. We actually use about 12 of these devices, but we can actually separate these 2 electron bunches and actually send them through the undulators. Then we need to actually delay well, in this case, the hard X-ray one, by using a 4-bounce crystal system, because light travels about a foot per nanosecond or 30 centimeters per nanosecond. If you want 5.4 nanoseconds, that's going to be a coffin that's about a little bit more than about 2 meters long. Crystals are great; they can reflect the beam, but they actually, imagine looking at a mirror and only seeing red light, but you change the angle and all of a sudden it's blue light, and that's what crystals do. So we can get high throughput but very narrow bandwidth. But we can overlap the 2, so this makes us have really good control over spectroscopy or using the hard X-rays as a probe. And we believe we can actually control the beams down to, as I said, the femtosecond regime. So what can we do with this? I saw the slide from Bob Shumline, but there's a lot of cool nonlinear spectroscopies you can think about. If you're looking at fluorescence, if you're looking at standard other setups, we can actually do simulated Raman, or instead of doing regular X-ray Raman, we can think about doing X-ray cars to actually look at element, and actually not only element, but chemical specificity on, like, for example, flames in gases, where we're looking at various species in the gas. And that's some of the cool, very basic four-wave mixing that we do with lasers all the time. We're thinking about doing these in X-rays. With the geometry, you can come in with a sample, like, for example, let's say we have a carbon sample, we can come in with 1.3 keV and a 1.6 keV with separation. You can actually calculate very easily with a phase matching where the car signal is going to go, and you can also figure out where the simulated Raman signal is going to go. It's just going to go down the lower and lower photon energy. Now, one interesting thing that I haven't mentioned is, if you think about the polarization and how that impacts it, if you just do basic Thomson scattering, you end up, if you do a gas of hydrogen or gas of electrons, you end up with some indifference frequencies and just basic Thomson scattering from these 2 X-ray sources, which could lead to a lot of unique spectroscopies. 2-photon absorption is rather cool. If you think about magnetic samples, you can now actually do, because of the selection rules, you can do K electrons to D orbitals, which means you can look at iron, nickel, and cobalt at 4 keV instead of the 700 eV, so we get better penetration if you want thicker magnetic samples and looking at magnetic dichroism. All sorts of nonlinearities matter under extreme conditions. You can actually think of like a wedge of samples where you have a carbon layer, of aluminum or silicon, and another carbon, and you actually individually excite the aluminum or silicon layer inside between like a sandwich of materials. You can think about indium gallium or any other multi atom system where you're actually triggering reactions on the specific atomic sites. And there's all sorts of unique spectroscopies that have analogs to lasers, but have never been done in the X-ray regime, and that's what we're hoping the instrument can do. Additionally, as I said, this will be a forward scattering because there's a lot of techniques that want to use forward scattering. It's useful for biology. the elevator pitch for LCLS-I was we can actually look at one molecule at a time. Instead of making crystals, we can actually do biology on single molecules and actually get a movie of how these things move. Mike Minetti actually has done some movies on some very basic or very simplistic models, but we were looking at bigger things like proteins. Turns out when you do the math, you need, for a structure of 20 nanometer object, you need about 10 to the 4, 10 to the 5 frames of the frames, which at LCLS-I is not really possible. You really need the high repetition rate to do this diffraction, where you're actually diffracting from a single object and getting resolution, will get enough data signal to actually make a sub-nanometer structure on the biological system. This is great because if you can actually think about like a ribosome moving, we can actually do that. We can think about injecting a system where we're doing an antibiotic or some antiviral where we want to see something bind to a protein. I can actually probably watch that process. One molecule at a time and just collect enough data that we can actually reproduce this reaction. As I said, this is prior to COVID-19. TXI was supposed to come online in 2023. This will probably be pushed back a few months. But what I want to leave you with is the X-ray parameters. Please email me if you have any questions about TXI. If you're thinking about writing your mock proposal on it, let me know, and I will try. I can try to help you out as much as I can with answer any questions. But as I said, TXI is really being dedicated to X-ray pump, X-ray probe, and forward scattering the tender. So it looks like, Mike, you are. It looks like you're there, right?
Yes, I am. And we are just kind of peering down. If you want to take a look at what that looks like for you.
Yeah, so oops. So what you're seeing on the left is a hard X-ray branch line, which goes to the far hall. And you have, this is still the AMO hutch. There are two, you can actually see 3 yellowish orange caps. And we haven't installed the TXI, whoa.
Technical difficulties with this gimbal today.
No worries. We haven't installed the TXI beam pipes yet, but we have stands for equipment. Right where Mike Minetti's standing is kind of where the coffin will be for our 3 meter by 3 meter delay line, which is needed for this crystal system. That's a big gap. So we actually have to remove the hard X-ray beam pipe, and it goes almost all the way to the wall, which Peter is graciously giving me a space in his hutch. We have a few other diagnostics and slits, attenuators that are in Hutch 1. They right now, as I said, we have blocks just blocking the beam right now. Those will be opened up once we have the beam pipes in. And there's a door here, mostly so we can actually align our KB system. It's going right against the wall where Mike is standing. This is about a 3 meter long piece of granite that's about 1.5 meters wide. Once again, another coffin. It holds 4 mirrors, which is unique. I don't think there's another system in the world. As you can see, the beam comes out of those 2 points. If the KBs weren't there, it actually intersects directly in the center of the hutch for various reasons that have to do with how I tried to make the geometry work. In fact, it hits by center 1/3. Right now, we're installed. This is the hard X-ray line, transport line. And Mike is standing right where we will be having the end station. Those racks have already been installed because getting them in after we get all our equipment in is going to be impossible. So that's kind of the TXI hutch. It's relatively empty right now. It's full of stuff, Andy.
Well,
it's full of stuff, but not hardware for. I was once told there's 2 types of scientists. Scientists who look at a lab and that's empty and think of all the possibilities, and scientists who look at a lab that's empty and think, I should go into theory.
Yeah. Here's a note. Here's our visible line spectrometer here, our VLS spectrometer here. So it's getting ready and primed to get there in TMO for Peter.
Yeah. Yeah, so right now my hutch is being used slightly in the staging area.
Yeah.
Perfect. Thank you so much, Andy, for this great overview. I think in the interest of time, we have again to go on. There are still a few questions on the Q&A.
Yeah,
It would
I'll
be
try
great
to
if you could
those.
answer them. Thank you. And then we'll go to the XPP hutch, to Tim van Riel. And that will be the first hutch where there's actually already a lot of stuff in there. This hutch is more or less ready to go. So Tim, the stage is yours.
All right, thank you very much. I hope everyone can hear me. I will turn on my sharing my screen now. Let's see. Like this. Does this work? Can you see my slides?
Yes, I can.
Good. All right. Yeah. So I would like to introduce the X-ray pump probe end station, the XPP end station. Thank you for letting me talk here. This is a great opportunity to tell all these interested young people about what we do. So yeah, X-ray pump probe end station. If we start with an overview of LCLS, you've just heard about the 3 soft X-ray beamlines or tender X-ray beamlines, and these are the ones that have recently seen a gigantic upgrade, and that we're still all very excited to see what they're going to be, how they're going to perform, and see them in action. So this is what you've heard about, and now we're going to move on to the hard X-ray beamlines. Essentially, this is everything above approximately 5 kV. These are the remaining 5 beamlines that take this beam. For convenience, I will mention that the 4 beamlines, XPP, XCS, MFX, and CXI, are in the hard X-ray department. They're kind of for themselves. And MEC is on its own doing the extreme stuff that you'll also hear about. And I will be talking about XPP, but also XCS afterwards in the next session. And of course, we're very envious for all these LCLS-II upgrades that are hitting the soft X-ray beamlines. But for the hard X-ray beamlines, we're also seeing an upgrade at the same time here during the shutdown. Our undulators have been upgraded, and this allows us to reach a much higher energy now. So from the next run, we hope to get up to 25 kV and look forward to extending the range, where previously we could only do 11 kV. So these instruments for XPP instrument is targeted from 5 kV to 25 kV approximately. And I will go over some of the general parameters for that. All right, so the X-ray pump probe end station was really designed to be a versatile beamline for laser pump X-ray probe. That's been kind of the general gist. It has been one of the bigger beamline hutches with lots of room and lots of setup space also for laser setups. So it is really the versatile guinea pig end station, as we'll also come in on later. The laser setup allows anything in the typical harmonics for a TISAF laser, so 266, 400, 800, with very high powers, or anything in the OPA range up to from basically entire visible range to infrared range. And we also do experiments with terahertz, so basically any kind of electromagnetic radiation pump X-ray probe. And the X-rays, as I mentioned, have previously gone from 5 to 11 kV. We could do harmonics, but then we lose 2 orders of magnitude. So with this upgrade, we should now be able to get the fundamental, which allows us to get the millijoule pulses, the full juice LCLS pulses to arrive at our sample. At 120 hertz still, since this is the LCLS low rep rate warm accelerator. So of course, these beamlines have existed for a while now, 10 years. So they are also in function. We have been running them stably and continuously improving them over the years, which we'll also see on some of the next slides. And of course, being a free electron laser, at only 120 hertz, the pulses are stochastic in nature, and we do see jitter in both energy and time and pulse intensity, as well as pointing and things like that. So there's a definite need for good pulse-to-pulse beam diagnostics and timing diagnostics in order to get the most out of such free electron laser experiments. So that's also part of the beamline design. And along in this versatility of the beamline, we have a robot arm for mounting the detectors, which allows us free movement to move around these large area detectors. All right, so zooming in on the basic hutch, you can see that we basically have some beam path, and the beam pipe propagates in this direction and continues down to the far hole. if we look at this paper in Journal Synchrotron Radiation, you can see a general layout. And to simplify this, it's really that we have a lot of optics and diagnostics. Then we have some kind of interaction point, typically on a diffractometer, and then we have a detector mounted. And of course, the laser is coupled in from the side. We draw on this. We have our initial large offset monochromator. I'll talk about this on the following slide. Then we have all our optics and beam diagnostics. This includes slits, pointing monitors, intensity monitors, lenses, and then also the time tool. So for our X-ray laser timing diagnostic, that is I'll also come in on that on the following slide. Then we have the laser in-coupling, where we bring the laser into the same beam trajectory. Then we have the diffractometer. We have either a detector stack for a typical crystal diffractometer. We also have a kappa goniometer, as well as a number of other setups and stages. And as opposed to synchrotron experiments, we choose the specific setup in collaboration with our users in order to do these experiments best. So for your proposals, you can think of having a lot of degrees of freedom for a sample, and then of course in collaboration with your mentor, you can figure out which would be the best setup given at LCLS. And then finally, we have this robot arm with a detector. And across the hall, we have our control room, which we're also very fond of. So first of all, this is a large offset monochromator. So typically when you monochromize the beam, we have the pink beam going on in a direct line as this is LCLS, a linear accelerator. If you put in the mono, you would typically split out the beam at an angle. So what we have here is a double crystal monochromator with very thin diamond that allows us to transmit the beam, the direct beam, with 50% transmission and let another beamline use it. And then at the XPP, we can take out this thin slice, this 0.5 EV diamond crystal monochromized beam, and use that for experiments. And for efficiency and operation reasons, we have over the last years moved the majority of XPP experiments that use monochromatic beams. Where we've kept them here at XPP, but the ones that require pink beam might be better suited to be done at XCS, where we have, in the next slot, I will be talking about XCS, where we have mirrored some of the capabilities of XPP simply due to scheduling constraints. But basically, having this thin diamond monochromizer allows us to take part of the beam and use it at XPP, monochromatic, while using the rest of the beam, the pink beam, the 50 EV broad spectrum, at either CXI or MFX or XCS. All right, the next thing we have is this time tool, as I mentioned. So this is a spectral encoding. So basically, we take part of the laser that we use anyway, we chirp it, and then we pass it through a silicon nitride sample. And then depending on where the X-rays hit, at what time they hit on this sample, we can get an encoding of the arrival time. So basically, we just have this in all the time. It measured out an edge like you see here. And this allows us to, after the fact, to go in and reshuffle every single pulse at 120 Hertz and rebin the data to get the best time resolution. As was mentioned, we have probably 200 to 300 femtosecond jitter. So if you do not do this time sorting, you only have 300 femtosecond time resolution. With this time sorting, we end up being really limited by the X-ray and laser pulses, giving us something more like 60 femtosecond full width half-max. As you can see from this figure down here, that really shows how these oscillations appear once we rebin the data instead of just this weak edge that we would see otherwise. All right. Briefly on detectors, we use a large area detector for most experiments. We also have the options of small area detectors with better energy resolution, PIPS diodes for signals that are easy to measure, as well as optical cameras that, of course, can see X-rays if you put YAG screens or other phosphor screens in front of the camera. So, as I mentioned, the XPP end station is a versatile beamline. And this is also shown with the type of experiments that have been done at XPP. And basically, as I mentioned, the time tool was developed and tested and implemented at XPP, and then afterwards has moved to XPP, XCS, and CXI, and is also being implemented at MFX. The in-air protein crystallography it was initially developed at XPP also, and has now gotten an entire beamline for itself at MFX, as well as gas scattering experiments pioneered by Mike Minetti, your friendly camera guy around the hutches, who worked on this initially to make these molecular movies in gas phase, and that has now been moved to CXI to get lower backgrounds for these type of measurements. So as you can see, there's a lot of kind of test experiments going on at XPP that then, where there's more space, there's more room to implement some setups and test setups. And then once they have proven successful, they have then been implemented in the more static, more different beamlines. So that is a huge advantage. And then some scientific examples. Basically, this is the first one that I also showed you for the time tool. It's really the coherent bismuth oscillations. This is really just looking at a diffraction peak as you pump the sample with the laser and change the time delay. And then you'll see the intensity change as you modulate the crystal, the form factor through the pump event, basically the phonons in the crystal. Another example is the phonon dispersion mapping. So basically, instead of looking at a Bragg peak, but using this large area detector to measure between the Bragg peaks, you can see a periodic modulation of the diffuse scattering. And this really allows you to map out the phonon dispersion of a sample after a pumping event. So as you can see, the majority of experiments at XPP are targeted towards some kind of laser pump X-ray probe, and that's really what it's designed for, to utilize the ultra-fast time resolution we have available at the LCLS. Finally, the conclusion for XPP, just briefly, right? It's a versatile end station. It's designed for laser pump X-ray probe experiments in the hard X-ray regime. This is 5 to 25 kV. Typically probed with in either scattering diffraction or spectroscopies. The X-ray parameters are now preferred in the monochromatic. So ideally we do monochromatic experiments at XPP, but of course with a good proposal, you are welcome to target pink beam full Sarset beam operation at XPP. We have a channel cut mono for scannable X-ray energy. And in general, the pulses are around 40 femtosecond and with 20 eV bandwidth, 0.2%. And the beam can be focused down to 2 micron with beryllium lenses and 120 hertz operation. Of course, we can run shorter pulses with some of these exotic modes that the facility can run in, but I've chosen to focus on the standard performance here. The laser parameters are really also 40 femtoseconds anywhere in the visible to IR range, also at 120 hertz, with typically plenty of laser power that you would want. This is, if you focus this down, you would start melting your samples typically, which is something you might be worried about. And then, of course, the time resolution for a typical setup where you're not geometry limited, the laser is these 40 femtosecond, X-ray is 40 femtosecond, and that then means that the time tool resolution is 10 femtosecond, so that gives you a 60 femtosecond full width half max response, showcasing the type of phenomena you can resolve. That's basically it. Any questions? And
Thank you very much, Tim. Let's have a quick look at the hutch, because there's actually something to see here. So if you could stop your slide sharing.
Yes.
And there is Mike.
Yes.
So here we got, here, Tim, talk away here.
Okay, well, so this is the large offset monochromator. So this is in here where the thin diamond lives, and then splits off part of the beam. So out of the offset trajectory, basically here, 1 meter to the side of the direct beam, we get the monochromatic beam, which goes down to our interaction point. Here you see the long array of diagnostics and different screens and monitors and things like that. If we stop here, we have the time tool and basically the red bridge here on the left. If we can go to the red bridge, Mike. This red bridge is our Bay bridge. That comes down when the laser is on. And then the laser crosses over here and is intersected with the X-rays to do this timing diagnostics in this chamber here, and goes into a spectrometer on the other side to give us our time stamping. And then basically we have a number of different diagnostics and things on the way up to the laser in coupling up here, where we then couple in the laser comes from this big cabinet on the left, which has a lot of stuff in it for different conversions and diagnostic also, and stuff, manipulating of the laser beam. This is the laser in-coupling box where we shoot the laser in from the side, hit a narrow, tight angle optic, and really couple in the laser collinearly, as collinear as we can, a couple of degrees, with the X-ray beam. And then the green thing here in the ceiling is the robot arm, where right now there's no detector mounted on, but this is where we mount our large area detector, or a smaller area detector, but the large one is about 20 centimeter by 20 centimeter, and really allows us to measure the diffracted spots or the diffuse scattering. It can measure up to 10,000 photons per pixels per shot, which means typically you can't put the direct beam on it, so that has to go through a hole in the middle, but otherwise it gives good dynamic range to measure the entirety of the beam. Yeah, I think that's in general it. You can see this is a functioning beamline, so there's a lot of stuff. The whole beamline is designed to shift over 1 meter to the side, but that is something we try to do only rarely, because of course it requires everything to be realigned. But basically it can be shifted from this monochromatic trajectory into the pink beam trajectory, which right now has beam pipes that lead onto the far hole and the next beam lines.
Perfect. Thanks very much. Mike, you could maybe just stay on and slowly walk through the X-ray transport tunnel between the soft X-ray hatches and the hard X-ray hatches. So that's kind of a little bit of a walk, but it's nice to see. This is currently preferentially, I guess, a storage space for all type of equipment, which we will need again when LCLS comes online. Back online. And in the meantime, I could ask you some more questions from the audience, Tim. The first question is, how does it compare to the CXI hatch if somebody wants to do time-resolved experiments on protein samples like light harvesting complexes? I'm sorry.
So of course there will be more on both the MFX and the CXI beamline later. Both the MFX and CXI beamlines are really designed for protein crystallography. So unless you really wanted to do something unique from XPP, which would be, for example, terahertz pumping of proteins, I would prefer, or everyone would probably recommend that you apply for beam time at MFX or CXI, since these are the beamlines that have standardized setups for that.
Thank you. Another question is the X-ray broadband or very narrow band?
The X-ray is narrow band compared to the pink beam at synchrotron, but compared to the monochromized beam, right? So basically the full envelope of the SARSA beam is 50 EV at 9.5 kV. And then of course, once we monochromate it, we have half an EV, typically from a diamond or a silicon.
Great. And then a last question, at least so far, what is the repetition rate of the optical lasers at the XPP end station?
The optical lasers are at 120 hertz also. So yeah, we run everything at the same rep rate. 120 hertz is also what we target with our detectors and cameras and diagnostics and all that. And that, of course, is something that will change with future upgrades where we move towards megahertz, but right now everything is still 120 hertz.
Perfect. And I think Mike's Wi-Fi probably dropped out in the middle. So the X-ray transport tunnel is where we identified some Wi-Fi issues, but we are back now, apparently.
Are you back? Okay, good. Yeah, I decided to
Yes.
switch to Slack as opposed to that edgy room.
Oh, I see. Okay, okay, perfect.
Got some controls work going on. Hello, sir. X-ray summer school.
That's right.
Getting it going. It takes a village.
It does. Yes, and conveniently.
The interesting thing here to see here, pardon me, Thomas, is
sure.
If I can do this, all the different tubes for the hard X-ray lines, we can kind of see. So I'm hanging right over the MEC hutch, or I'm sorry, the MEC tube, and then MFX and CXI and XCS, all these different types of hutch, the tubes, and the nice, beautifully color-coded stands. A hallmark of LCLS.
Yes, and now we probably have a drop out of Wi-Fi again. That was sort of expected. Ah, there we are back.
Yeah.
So this we just walked by is a copy of the large offset monochromator that we saw at XPP, and this is the equivalent of that just for XCS instead. So it's basically the exact same design. There's a thin diamond in here, and this allows us to take and actually split another part of the beam off. So technically we can do experiments at an additional beamline if we use this. Of course, there's transmission losses every time, and it complicates experiments, but in principle we can do that.
Right. You can kind of see the fanning out of the beam pipes, everyone. And then here is the X-ray split and delay, newly revamped for hard X-ray ops.
So where you can make 2 X-ray pulses out of 1.
I will briefly introduce this in the XCS session, the next
All
session.
right.
Yeah, that's the convenience
Well,
of
here
the
we
set.
are, Tim.
Yep, home sweet home.
There you go. Home sweet home.
Yeah, Tim will also give the presentation for the XCS end station, so that's actually quite fitting. He can just stay online. That's the XCS control room. And here we are in the hutch.
Yeah, so right before COVID-19, I was preparing to do test experiments. So that's why the roll-up doors are closed down and everything. I was ready to do laser-only test experiments for our new setups. So it's a little bit messy. We have, this is a portable spectrometer that's in the way. That's Takahiro that's working on that. It's basically for characterizing the energy spectrum of the X-ray pulses on a pulse-to-pulse basis. The setup that's currently in place is the liquid setup. It might have been moved because I know our engineer was working on repairing some pieces that we need ready for the run 18 startup. So yeah.
And here we go. Now we have the Bay Bridge.
Now we have the Bay Bridge instead, exactly. And this is the equivalent. Well, not the equivalent because this one transports the beam that we use for everything for the experiment, and then the beam that is used for timing is split off on this optical table. So on this table we do all manipulation of the beam. Basically, we get the 800 nanometer through the Bay Bridge, and then on here we do harmonic doubling or OPA work and timing and all those things. We do that and couple it into the setup. But yeah, I'll be talking about this in the next one, I guess. So I'll leave that.
So in principle, we can just start that now. So if you want to start sharing your slides again.
Absolutely.
Perfect. And there were some small issues with your last set of slides. There was some black bars on the screen, not in the center, so that therefore it wasn't really a problem. But it seems like Zoom is in front.
That might be the case. If I do this, is it better now without any?
Now the big bar is gone. The rest is probably the rest was not so severe. Yeah.
Yeah, there's one I think is Zoom. I'm worried if I close it, I'll close Zoom entirely. What happens if I'm not going to do that. That would be stupid. All right, so on to the purple beamline.
We don't see your slides at the moment.
You don't see it?
No, we see your PowerPoint.
I see my PowerPoint. Okay, I'll stop and start again. Let's see here. Share screen. PowerPoint slideshow. Do you see something now?
Yes, the slides work, and the bars are there are some bars, but it's not very severe. So
how do you throw away these bars? That's weird.
I think it's sort of a Zoom malfunction or something.
Yeah. Okay. All right. So XCS. XCS is the fourth, now it's fifth beamline because they're the soft X-ray beamlines, but the second in the array of hard X-ray beamlines. XCS is short for X-ray correlation spectroscopy end station, and that's really because the XCS beamline was initially designed for X-ray photocorrelation spectroscopy. However, it has been further upgraded and amended to include many other types of experiments now. So yeah, basically the Beamline was for XPCS, but now really includes also the X-ray split and delay, which is also for XPCS, but also the solution phase chemistry pump probe experiments that used to be done at XPP have now been moved to XCS because they like to use the full SASA beam, the pink beam. And in order for this optimization of the scheduling, if we do the experiments further downstream at XCS, then we can run monochromatic experiments at XPP at the same time, effectively doubling our amount of beam time available for users, which means more experiments. The laser is a little bit less advanced setup than at XPP, but basically in the visible range, so 266 to 800 nanometer, we now have both the harmonics and the OPA that allows us to do short pulse excitation, similar to the X-ray laser pump X-ray probe that I talked about for XPP. The original design was these 5 to 11 kV. Of course, now it's 5 to 25, and similar to XPP, it's 40 femtosecond a second and around 2 millijoule pulses, 4 millijoule on a good day. And as we approach the 2025 kV, we expect it to be around a millijoule or below. And of course, again, pulse by pulse beam and timing diagnostics, as well as detectors, since all analysis at LCLS, at least at 120 hertz, really requires a shot by shot analysis. And then here we do not have a fancy robot arm like at XPP, so we're limited to mounting our detectors on stages. For the liquid chemistry experiments, we typically do a stage stack with XYZ motion, but of course that doesn't give you full freedom as with a robot arm. All right, this is approximately what the Beamline looks like. I added this gray wall to show you where the limits are, and then basically the split and delay, which I will be talking about, what we saw when we walked through the hall, that is on the other side of this wall. And then we have the laser, which was newly added a couple of years ago, really allowing us to get this visible laser, pump laser in at 120 hertz, similar to XPP, to do laser pump experiments here. And of course, we have this very large vacuum tube or helium tube, however you choose to use it, typically vacuum, that allows you to measure diffraction spots or diffuse scattering, whatever you want to do, speckle at very long distances. And this is typically needed for X-ray photocorrelation spectroscopy. You would want to go to long distances. And that's really why this is at this Beamline. But for any of the XPP-like pump probe experiments, we would typically not use the arm. We would move it out of the way, and we would just mount the stage right after the diffractometer. Typically for diffuse scattering, I like 5 centimeter detector distance, so there's no need for this 7 meter arm. Again, we have a drawing of the stuff, but it's really, we have the large offset mono that you saw, which is far back. We have the optics and diagnostics. Then we have the time tool on the laser table, the laser in coupling right before the sample to get the laser in as narrow an angle as possible, the diffractometer, which holds the sample, and then a mounted detector. And typically would either have the detector close to the diffractometer or at the end of this arm that can be moved at different distances and different angles, of course. All right. Then I will talk about this fancy split and delay that you saw on the way. This is basically a helium box that uses crystal optics to split the beam spatially. So it splits it by cutting it in half. So basically we move in a crystal so that it cuts the beam exactly in half. And then we lead the one part of the beam on one 4-bounce trip, and we lead the other part of the beam on another 4-bounce trip. And then we combine them in the end again. As you may imagine, for any of you that have worked with crystal optics before, getting something stable to run with these multiple bounces, especially for a 120 hertz machine with intensity and thermal fluctuations, this can be very hard. And then, of course, in addition, we want to be able to scan the delay. That's the whole point. So basically, 2 of these crystals can be moved away to increase the path length and thereby change the delay between these 2 pulses that we have overlapped afterwards. This has taken a lot of effort, and I'm presenting it because there are a lot of experiments that are utilizing this now, or attempting to in the last run, where we basically only had it available. And it really is at the point where we haven't really done interesting science with this yet, but we have proven that we get nice overlapped pulses and that they interact. So what you see here on the side, these fringes are from the X-ray pulses interacting with themselves, creating these this spatial periodic frequency. If we change the delay ever so slightly, as soon as we're outside the envelope of the X-ray pulse, there would no longer be any fringes. They would not interfere. So this only happens, as you see from this time scan, within these 16 femtoseconds where the X-ray pulses are overlapped. But the stability of this setup is very hard, and getting them perfectly overlapped is also hard. So, but still a very interesting type of experiment you can do, and very unique capabilities for the XCS Beamline. The other thing, as I mentioned, is this liquid standard configuration. And I know that there are, I think, a couple of mentoring groups that will be focusing on this, which is one of our standard configurations. Standard configurations are identified to try to fix the setup as much as possible, so we don't have to rebuild everything for every experiment. And then allow some minor modifications, but not major modifications, in order to help the useful time during an experiment. The idea here is really to have a liquid jet, to pump it with an optical laser, and to look at it with one of 3 different techniques, either through scattering, diffuse scattering, to study the structure, X-ray emission spectroscopy to study the spin charge, or X-ray absorption spectroscopy to study the structure charge. So for X-ray diffuse scattering, we measure the diffuse scattering on the large area detector right after the sample, and then analyze that to say something about the molecular dynamics, the photo-induced molecular dynamics on the chemistry that's in this liquid jet. The XCS measures the prototypical emission spectra. The KH typically is what we target to identify the charge or spin of the chemical compound of interest and the photo-induced changes of that. And the X-ray absorption spectroscopy really is typically either done in the pre-edge or in the edge region, in the X-abs region, to get either the electronic structure or the structure of the sample through analysis. However, the scattering and emission can be done simultaneously with a pink beam, but the absorption really requires a scannable monochromatic beam. So typically these experiments are done on their own. And then, of course, mentioning this energy upgrade that allows us to go to 25 kV, just to show a typical periodic table. Until now, we've had access to the K edges of these elements, basically transition, third row transition metal, transition metals that we're interested in. So this is the stuff like iron, cobalt, and nickel and copper, which are luckily very interesting. But now with this upgrade, we really extend the K range up to 25 kV, which means we can access a huge number of other elements. And the L edges, of course, include a lot of other elements. And this is both for X-ray absorption spectroscopy and X-ray emission spectroscopy. The K edges are typically a little bit easier to analyze and assign. The L edges are a little bit more complex, but just having the ability to access all these is a huge advantage, especially since they can be done simultaneously with the X-ray diffuse scattering. So you can really track independently the 2 things at the same time in the same measurements, making the analysis much more robust. Again, the detectors that I mentioned earlier, we have the same availability. These are in the LCLS detector pool. And since this is all in hard X-ray, we really have the same large area, smaller area with better energy resolution, diodes or optical cameras, and we can place them as we see fit. Typically for the scattering emission combination, we would use a large area detector for the scattering and a small, better energy resolved EPIX 100 here for the X-ray emission spectroscopy. And then for the science examples, as I mentioned, the split and delay, we hope to be able to do X-ray photocorrelation spectroscopy, really to start studying the disordered dynamics of systems such as solution phase systems. So that would be really, really interesting. But we're still at an early point in that. And then, of course, the solution phase chemical dynamics, which have been really well worked out over the last 10 years, developed at XPP, now moved to XCS, and are really at a point where you by choosing a good sample that can be dissolved at good enough concentrations and excited with an optical pulse, you can really start saying something about the mechanism of these photoexcitations and really track the structural change and the spin change through this excited state potential energy landscape for a given molecule as a function of time with 60 femtosecond time resolution, which is really something new in this field. Basically, the summary is very similar to XPP. The addition is, of course, there's this 7-meter large angle detector arm, which allows you to measure speckles at very long distances with relatively low background through helium. And then, of course, with the upgrade, we can go to these 25 keV energies. The experiments are typically in air or in helium to minimize the background, since hard X-ray don't really require a vacuum. So this makes it much easier to alter the setups and modify the setups either during the experiment or before the experiment, and that gives us some more versatility. The X-ray parameters are again the same, but for the XPP, we prefer to use this monochromatic beam, whereas XCS is really for any of these pink, mono, or the channel cut for scannable energies. The laser parameters do not include the infrared, but otherwise in the visible range are the same, and the time resolution are the same. When mentioning the time resolution, I would say that, of course, this depends on the geometry. So for this time resolution is also for liquid samples, this is given by the velocity mismatch in the liquid jet. So basically, as the laser propagates and the X-rays propagate at approximately the speed of light, and the laser actually doesn't because of the index of refraction of the liquid. So you do get approximately a 1.1 femtosecond smear per micron in water. So the 60 femtosecond is really what we can get for a 30 micron liquid jet, and if you ran a thicker jet, you could do that, but that would be at a cost of time resolution. All right, and that was what I had for XCS.
Perfect. Thank you so much. You had a lot of things to present. What is your feeling? Do you want to switch back to Mike's video, or did you already show everything?
No, let's quickly go to Mike's video since he's there.
Okay.
And, have a look.
All right.
Yeah. So basically, on the floor, you can see these long tracks, which is all in place just to move this large angle detector mover with high precision, so we can really get it in place and aligned, and then we would place the detector at the end of this long tube. It's a little bit of a hassle when you don't want to use it. So as you see right now, it's really moved into the direct beam direction and tried to move out of the way. We still have to manage with all these rails in the floor. But other than that, of course, they don't prevent us from utilizing the interaction point in that region around it. And now for the upcoming run, we will have some new stuff in place around the goniometer. So we will have a cage and some more stage mounts ready at the interaction point to really allow for more complex setups and more stable setups. It all looks a little bit messy. I apologize. This is often the nature of experiments. We typically clean up when there's important tours going on. I think we would usually have cleaned up for the summer school, but since we're not allowed on site, it's very hard for me to do remotely. And even the beamlines with the robot arms cannot be programmed to clean up the beamlines, sadly. So yeah, it's a rather big hutch we have here but mainly it's really for a lot of it for storage at the moment, but otherwise for this large angle mover, which is really only used for a subset of our experiments. And then this is here we have roll-up doors leading into the MFX beamline, and also on the wall there's a water dump preventing our beam from accidentally going into the next control hutch while people are working in there. So this big metal box is filled with water, and that will take some time for the beam to drill through in case it was hitting the wall. And then of course we have our control room right next to the hutch in this case. This is where we actually do the experiments, and this is where we simply sit with our users and run the experiments with all the screens to monitor, control, analyze, and quickly make decisions for these experiments, since of course they have limited time to actually be done.
Yeah, and maybe one interesting information is that these hatches are always closed if the beam is on, so you have to remote control your experiment.
Absolutely. You do not want to be hit by the X-ray beams, so there are big lead doors that prevent you from that happening. You have to interlock. Even the lasers are not just turned on. So we close the doors or close the blinds to be able to do laser work or X-ray work, and then we have to remote control everything. And that also means that you have to do a good work of planning your experiment and setting everything up right, because it can cost a lot of time if you need to go in to move things physically.
Perfect. Thank you again, Tim. That was a lot of talking, as I already said. Could you maybe stay on 1 or 2 more minutes and answer the questions from the Q&A in writing? I've seen there are a number of questions. And then I would like to switch over to Ray for MFX. So Ray, if you want to start sharing your screen. Very nice background.
All right, should I address the questions?
If you could just answer them in writing,
okay,
just in,
sure,
in the interest of time. Thank you very
Absolutely.
much.
Go ahead. Sorry for going over time.
Oh, no worries.
Hey guys, can you see the screen?
Yes, we can.
Yes.
Okay, perfect. That's the COVID question. Can you see my screen? So I will be talking about Hutch 4.5, the MFX instrument, macromolecular femtosecond crystallography. This is sort of the bio portion of the tour. Meng will be talking about CXI after this. So these two hutches are where a lot of the bio experiments happen. MFX is actually the 7th hutch, the last one that has been opened, but you'll see why in a moment. We call it 4.5. It was kind of squeezed in between 4 and 5, and we're very clever. For anyone that has to go grab a sandwich or go to the restroom or needs to nod off really quick, this is a quick TLDR. You want to screenshot it or something, hold on to it. But essentially, MFX is if you want to think about a baby XPP, right? Tim did a really nice job explaining XPP, and it's kind of a smaller version of that to kind of focus on bio experiments at the LCLS, primarily SFX. And so we'll talk about that a bit here. Here's some of the specs, but we'll just kind of jump into it. It's a bio-focused experiment that is really focused on these versatile end station geometries where you can mix things. This kind of feels like an 80s retro pic of what we'll start to see in person soon. But really the key is having these modular end stations to do in atmosphere kind of experiments. So doing bio, I know this is kind of everyone's first day at the summer school, so you guys haven't heard a lot of the spiels and lectures yet. So I'll give a brief primer. What can we do with bio with our X-rays? So for example, what's going on in the news lately? The coronavirus is a hot topic. And if we kind of look at classic coronavirus, the first one, we learned that the coronavirus, grab the laser pointer here. In its membrane, it has a spike protein, right, that binds to the ACE2 receptor in human cells, right? So if we can understand the structure more of this glycoprotein here on the outside of these coronavirus capsids, we can maybe understand something new. How do we block it? How do we prevent this, and so on? So actually, a group from University of Washington very recently in May published this work where they went to the synchrotron ALS out in Berkeley, and along with some cryo-EM studies and some other in-lab studies, they were able to determine some promising antibodies. So this S309 antibody actually looked pretty promising to bind to this spike protein in the coronavirus and might lead to a more generalized kind of antibody, because they saw that in the structure, the high resolution structure that they were able to combine with the synchrotron data and the cryo-EM data, they were able to see that this binds well to many different variations of the coronavirus, for example. And so now a lot of the clinical trials that are going on are moving forward and looking maybe more specifically at these S309 antibodies to sort of design them as a drug target, for example. So these high resolution structures can be really powerful, right? So SFX, I'll use that acronym a bit, serial femtosecond crystallography. This is sort of the main workhorse of the biology at LCLS or at an XFEL, for example. So Giorgio did a nice talk this morning talking about synchrotrons. And if you took, or actually most of the protein structures that we know as a community, 80 to 90% of those known structures come from X-ray crystallography, from like synchrotrons and cryogenic macromolecular crystallography. So those synchrotrons take these 10 to the 12 photons and they dose the sample in about a second. So you start to see as the photons come in, they start to give data and information, but as the later photons come in, they might start imaging damaged data. So that's why you have to do like a cryogenic experiment to sort of mitigate that radiation damage. So a place like LCLS, they take those the same 10 to the 12 photons, and they focus them down and deliver them in about 10 to 100 femtosecond pulses. So you get this diffract before destroy idea. And, you know, for those of you familiar with lightning and thunder, you know, you see the lightning before you hear the thunder, a speed of light versus a speed of sound phenomenon. So you get your information in and out before the damage begins to propagate. So you hear a lot of us talk about in biology, this diffract before destroy, or these radiation damage free structures. And then because of that, you don't have to probe your sample at cryogenic temperatures to mitigate the radiation damage. You can now get more room temperature or, you know, ambient temperature structures. Because of this as well, it's not frozen. You can study dynamics and maybe look for structural intermediates. And you can maybe even probe smaller crystals. This image above is sort of the dream, a single particle imaging, something you might do at Andy's TXI instrument, for example, where you just take one object and you probe it with X-rays. But it's a tough experiment and we struggle with signal to noise. So one of the things that we do in protein crystallography is you align all those proteins in an ordered crystal lattice, and that sort of creates a signal amplifier and you get this protein crystal structure, right? One of the tough things about these experiments at an XFEL, and you'll see here on the right, is delivering the beam is non-trivial, right? The beam comes at 120 hertz. So we've spent a lot of time developing these different delivery methods. We heard Tim mention, you know, these liquid jets. And this is a liquid jet being hit by an XFEL, and you can see this high-speed image, you can see it exploding, and it creates a pretty violent explosion. Here's a droplet stream also being hit by the XFEL, being violently exploded. And so anything you kind of put in that beam path is not going to survive. So, you know, some of the initial things you might do is you take a fixed target and put it in the beam path. That's fine, but you have to replenish and put a new target in the way, and your old target, whatever was holding it, might be damaged. As you see in this little animation, you see the holes left behind. So you can't necessarily come back and probe the same thing. And then we have other liquid jets. This is a GDVN, you know, where it takes a sheath gas and focuses it down and puts it in the X-ray beam. So this is sort of getting at the idea that why we have all these complex geometries and so on at the end stations, because it's not trivial for your sample to get into the beam, right? So now you want to do a bioexperiment at LCLS, you're probably going to want to stick to higher energies or shorter wavelengths. So kind of the hard X-ray regime, you're not going to want to do it. Sorry, I put here AMO and SXR. Those are the old soft X-ray instruments. They no longer exist. But you wouldn't want to do this at a soft X-ray instrument. You're going to limit yourself, for example, with the available resolution. You want to get resolutions on the order of single angstroms, ideally, maybe 3 angstroms, for example. And so you want these higher energies. And then also the soft X-ray experiments, you know, they interact with a lot of stuff. So you're going to need to be in vacuum. And so you don't want to limit yourself that way. That's kind of implying vacuum sucks. It makes the experiments a lot harder if you don't need it. A lot of those liquids, gases, proteins, salts, all those things that are sort of inherent in a biological experiment, none of them want to be in vacuum. And so if you don't need to do it there, don't do it there. So that kind of limits some of the experimental end stations you want to do your bioexperiment in. CXI is a good one, but it's in vacuum. So, you know, if you don't want to do it there. And then if you want to maximize resources. So kind of implied in some of these talks is that LCLS is not like a synchrotron. It's not like the town watering hole where everyone opens their instrument and gets a photon. One instrument kind of gets it all at once. And we've, over the past few years, have gotten clever in doing things like what we call multiplexing, where, like Tim was talking about, you can sort of take a sliver of the beam and keep it and send the rest of the beam down to the far hall. So when those SFX experiments were first being tested out in XPP, that was great. And they sort of, were becoming pretty lucrative for the biology. They didn't have problems with injection failures and so on at CXI. They're having good success here, but then the beam stops at XPP. So we can't do some of the clever multiplexing experiments that we'd like to do. And XPP and XES and even MEC, they're all very highly specialized things not to do a biological experiment. So we had an idea where XES had a lot of space back here. We had a closet that was kind of empty. So we needed our hero in the closet by the stairs. And somebody said that we should turn that into a new hutch, the 7th hutch, hutch 4.5. So we took that space, retrofitted, slapped up that wall. You guys saw the Hello Kitty door that showed up there. And we made the new bio-focused MFX end station. And what's really useful about this is now you have all the bio experiments can sort of move to that beamline, and you at the same time expand access. So now those bio experiments aren't being scheduled maybe so much at CXI, some still are, but now they move away from XPP, and now XPP can continue to send the beam down to the far hall. And so now we can maybe do 2 experiments at once. So now this is sort of that same beam layout, right? And now they can continue doing experiments, send things down towards the far hall, but now we move the mirror further in and we kick the beam over to MFX, and we can now focus on, just the bio experiment. So like I said, MFX is a very basic instrument, like an XPP redux. Instead of green, it's orange and it's smaller, but it has, this very modular sample table that you can sort of add your own specific end station experiment ideas. You have the big detector arm, which we'll see when we hand over to Mike, and then we have a detector mover. Since we are limited in space, one of the things that we need is X-ray optics that can kind of work in that small space. So we have what's called a transfocator. It sounds like a transformer that studied optics in college. But this transfocator is just a stacks of compound refractive lenses. If you guys are familiar with X-ray optics, or you might be in the next week, X-rays are kind of annoying in that they need, everything is opposite. Their index of refraction is slightly less than 1. So refractive lenses focus, and they focus slowly. Other beam lines like CXI and maybe TXI, they're going to have KB mirrors, which are slightly different. The CRLs here are very chromatic. And so you can take in a lot of different wavelengths, but then because of that, it changes your focal point. So the transfocator moves so that when you switch X-ray energies, we're typically at 9.5 kV, for example, in MFX. But when you might want to swap to a different energy, you keep it at the same interaction point at the sample table. You don't have to be moving the sample table detector and all that. You just move your transfocator back and forth a few millimeters, a few centimeters, depending on the shift. And then we also have a set of lenses in the back to pre-focus to sort of optimize that transmission into the transfocator. So you can get a nice tight spot, about 3 microns at the interaction point. So some of the things we might not see on the tour, but we sort of have 4 kind of standard configs end stations at MFX. The main one, the one that like we can sort of support on our own is this Hera box. It's a helium-rich environment. And here we can put all of our liquid jets. So if you do a literature search or anything like that, you can see that we have all this different liquid jets that we can do. And all the things that you might have done at a CXI, you can bring forward to an MFX, same thing with XVP and backwards. These other configurations, we can support, and we typically do, but that you might have to collaborate with their users. So we have a typical goniometer with the SSRL's SMB group, Ina Cohen, for example. This is, if you've ever done a synchrotron experiment, mounted on a loop or on some crystal mount, and you do the kind of rock, you're not going to rock faster than 100 femtoseconds. But you can kind of do that fixed target experiment. Alchemeets from CFEL has done a faster scan, 120 hertz. And again, you sort of load a chip with your fixed targets and run through it. Then This is a really cool one. The GIF is nice, but you have this droplet on tape. All these droplets are put onto a capped on tape. And then kind of like in an assembly line, they get probed by a laser, and you know their spacing, their distance, the speed of the tape. And so you get a different timing, and then they ultimately get probed by the X-ray source. And you have a, multiple pump probe delay kind of system. So this droplet on tape was sort of spearheaded by Franklin Fuller and the Berkeley group, Lawrence Berkeley group. And it's a nice job in that same system with I assume a slight modification, but you can put a reaction chamber. So instead of studying light activated systems, you can study gas activated systems. So you pass it through and you can put it in an oxygen rich environment, and you can study sort of reaction centers that are sensitive to oxygen. Maybe you can change that gas, maybe a CO2 sensitive or a nitrogen sensitive kind of experiment. So it's very modular. It's kind of, because of MFX and this sort of open air design, we can do simultaneous diffraction for the crystallography and emission spectra. So you can study sort of the electronic state of the binding center. A lot of these binding sites have metals that are more sensitive than the surrounding molecules. And so you can study their state and kind of know that they were in the correct state, their excited state, some intermediate state. So you can do that with the droplet on tape. So those are the 4 things. They're kind of quick, but we might not see them all there. The liquid jets is 1, the goniometer is 2, the fast scanning goniometer is 3, and then this droplet on tape system is 4. They're just different ways of getting your sample into the beam. And then finally, I'll end it just with some brief science, but some of the really cool things that are coming out and sort of the big promises with a lot of these bio experiments is seeing the molecular movies, but also finding structural intermediates. So we have a few experiments here, which we'll likely talk about maybe more specifically in our subgroups, but finding photosystem 2, how it splits water. A lot of that work has been really fleshed out on that droplet on tape system. And we're learning more and more about that reaction center, that manganese cluster, cytochrome C oxidase, because of the room temperature, the room temperature radiation damage free structures that they found at MFX. They were actually able to find that there's a new water molecule that was hanging around at this catalytic site, seeing some of this side chain motion that they weren't able to see before at a cryogenically frozen state. And we were also able to follow a reaction of another enzyme with simulation and with actual data and confirm it, things that are very rarely seen. So these are some of the cool experiments, these mixing experiments and structural intermediate kind of things that we can study at an MFX. You can also study them at a CXI, for example, but like I said, these experiments get very complicated putting them into a vacuum chamber. And so if you can put them in a more modular open air system, you really benefit and have more success. And so I'm going to wrap that up. I wanted to show one quick thing about the jets that somebody asked about in ChemRix. These are just thin liquid sheets. I will point to the publication and Jake Korlek, reach out to him and ask him questions, but this is really cool stuff. And they're very thin, 100 nanometer thin jets to study your things. So one more time for the people that didn't screenshot fast enough, and we can maybe cut over to Mike.
Perfect. If you could send me your slides, then I can also make them available to the students. Could you stop sharing your screen? Then we can see Mike.
All right, so we're in MFX. Mike, can you turn back and look at the control room?
Sure.
It really was a closet, so it's very tiny, guys. No social distancing in here. So this, again, we have to be external. And so now when you walk in to the hutch, and you can see our color's orange, you can see there's the robot arm at the top. The table is right below it. The detector, this is a Rayonics 340 that's to the left here. And that is also on a stage, and it can move forward and reach the interaction region. That should be the alignment laser.
Yes, it is.
And so if you look to the right, this is actually the Hera box. And so inside this Hera box, you'll be able to see, oh, perfect. So you can see that sort of metal cone there coming from the right. That's sort of a collimator to clean up the beam that's coming in from right to left. There's actually a little sample injector, a little capillary in the beam. That's what's glowing that green light. And that's where your sample would go. That's a few hundred microns. And so your sample will get hit, it will diffract towards the left and you get your data. These cameras here on the bottom right of the screen are to image and to make sure that we're putting things on the right spot. If you look to your right, those are the diagnostics and the beam optics. This is a new laser enclosure that was there to the right. Might just cut under the beam pipes. So there's some last minute slits. And the famous transvocator, there it is. You can see that stage at the bottom to move it back and forth. Different beryllium lenses can be dropped in to give you the right focus, and it'll move back and forth to send the beam towards the right at the right focal length. But yeah, it's a pretty basic touch. Right behind us, this new femtosecond laser enclosure. Interns actually designed and built all this last year, which is really nice.
Awesome.
So again, we're trying to match the XPP capabilities. We can do laser pump probe experiments, but we didn't have a femtosecond laser. So now we're bringing that up, and hopefully soon enough it'll be ready for all those experiments.
Perfect. Thank you very much. We are a little bit over time, so there are also no questions at the moment, but maybe you could also stay a little bit longer on the Zoom call and see if there are more coming up.
Yep.
And then I would hand over to Meng Liang, who I can already see. Meng, please share your slides.
Sure.
Awesome.
Gentlemen,
People see my slides?
Yes.
Yes.
Great, thank you. So I will be talking about CXI, that's the Coherent X-ray Imaging instrument. It's the red one and the fifth one, according to the convention of LCLS. So here, what you'll see is you will see a schematic of it. Let me see if I can show laser pointer. So CXI essentially has this layout. We have two sets of KB optics in the front and three sample chambers or interaction regions where you can do experiments. So CXI is the hard X-ray forward scattering in vacuum, high energy density instrument. I know that's kind of a lot in one instrument. I'll try to explain what all of those mean. So what I mean by the fact that there are three sample chambers is because we have two fixed curvature KB lenses. So these are fixed and they are not bendable like the ones you heard earlier in terms of the soft X-ray instruments. These are fixed. And so of course that means the interaction region is fixed in a certain location. And so what that means is that we have multiple chambers in order to utilize all of these beams. There's a 1 micron focus that has a 1 micron beam that is focused by 1 micron KB mirrors, 100 nanometer focus. And we in addition have a parasitic serial sample chamber. And what this is that when the beam goes into the 1 micron focus, very often much of the beam is unscattered. And so that allows us an opportunity to utilize those unscattered X-rays. We will refocus them and utilize those X-rays to do a parasitic in parallel experiment in yet another chamber. So those are the three sample chambers of CXI. The whole beamline is actually movable, so it's on a specific rail. And so the rail can move based on which KB mirrors, or if we don't use KB mirrors, we can move it to the direct line. Each of the KB mirrors will deflect the beam both horizontally and vertically. And so it is important that we are able to move the entire beamline in order to utilize that beam. So the CXI optics that are kind of the jewel of CXI are these fixed curvature achromatic KB mirrors. We have two sets. And these are elliptical mirrors, and they have less than 1 nanometer figure height error, and actually less than a quarter of that in terms of roughness like error. So here you see a picture of the nanofocus KB mirrors. These very, very shiny pieces of silicon are what focus our X-rays into those specific sample environments. And so because our focus, these optics focus these X-rays into such a tight spot, it's actually very important to be able to characterize them. As you know, there is jitter, and then there is also just the difficulty in being able to align these mirrors properly for the different photon energies that we have. And so what we really need is to be able to characterize the beam very well. So in that, in light of that, we have developed, Matt Seberg has developed a way to do Talbot interferometry to characterize this beam profile. So one thing that we really wanted for it is a single shot capability. And so what we're trying to do is we're trying to characterize the beam that is incident on the sample. Of course, typically if you characterize like something, you actually can't use it. The great thing about Talbot interferometry is that one can put a grating after the sample itself. So this is the unscattered beam. And so you are able to use the Talbot effect to image this grating that has the wavefront kind of imprinted on it or modulated by it. And then by using some data analysis that requires lots and lots of Fourier transforms, you can actually back calculate what the wavefront was supposed to be. This is very critical for the 100 nanometer like focus, because as you can imagine, when all of the X-rays are focused into such a small spot, it is very difficult. Nothing will survive it. So no characterization can really be done on that like very easily. And so this will be able to allow us to both tune the mirrors in terms of this angle, so we don't bend like the mirrors, as I said, because they're fixed curvature, but we will tune the angle when we try to get the best like focus. And using this, we will be able to characterize like that focus to get the best one, and also be able to account for single shot jitter in terms of the spectrum or the position. And so this is a technology that we are currently putting into CXI in order to better utilize our 100 nanometer high photon flux environment. I also want to briefly talk about maybe a little bit more detail about the detectors that we use at like CXI. Tim has already mentioned that we use the CS pad. We are recently upgrading into the Jungfrau detector. And so I would just want to talk about the fact that these are charge integrating detectors, which are quite different from the single photon counting detectors that people from the synchrotron community are probably familiar with. Those would be the Pilatus or the Eiger. So one thing that is special about FEL detectors is that unlike the photon counting ones, where you have kind of an upper threshold into the number of photons that can be accurately counted. And so what happens for a single photon counting detector is that you have certain like thresholds, and then once the charge that is measured by detector exceeds a specific threshold, you count that as a specific number of photons. But because there's an upper one, you cannot very easily count accurately high photon fluxes on your detector or high signal levels. And so so something like if your maximum photons is like 10, if you have 100 like photons, it still counts it as 10. And so these charge integrating detectors, that technology really took off with FELs. And so those are the kind of detectors that we have, the CS pad and the Jungfrau. I want to point out is that not only is this good for FEL science, but also in terms of synchrotron science, where you have really high data signals. So things like protein crystallography, where you have Bragg peaks that are very, very high and very, very bright. And so what you really want, these charge integrating detectors have currently, kind of in the last few years, been moved to synchrotrons in order to do more accurate protein crystallography. So you can measure these incredibly bright Bragg peaks with much higher precision. So I will more or less skim over this because Ray already explained it so well. So we also do serial femtosecond crystallography. So at CXI, because we are in vacuum, we typically specialize in samples that have very weak signals. So whether that means they're very, very small crystals, they can be fibers, they can be, things where even the helium environment of MFX would really degrade the data quality. So for those experiments, you would go to CXI. But one thing that we also do at CXI beyond biology is we also do many things that utilize this high photon flux. So one thing is we explore nonlinear X-ray methods. So this is actually work done by our host, Thomas. And so what this does is that it actually utilizes the 100 nanometer like focus, so that's the highest flux density, in order to do population inversion in kind of these manganese salts, manganese complexes. And so what they do, what they have is they have stimulated X-ray like emission. So exactly kind of the population like inversion and the stimulated emission that you would have in a traditional like laser also happens here. And what this really does is it provides this elemental specificity, I'm sorry, I can't say that word, specificity, and also increased like increased sensitivity in terms of energy. So in terms of its non-linear response. So what you can see here in this curve is that you actually have this non-linear like regime where it actually saturates. And so what that means is that like all of these, you have a complete population inversion. There are no more states that are possible. And so you can really do very interesting things in terms of spectroscopy with these nonlinear techniques. Another type of experiment that we do is gas phase chemistry. This is actually the science of Mike Minetti, who is, our tour guide who's on site. And so what gas phase chemistry does is that it makes these molecular movies that you've heard probably a lot about from LCLS. And so what it is that you pump a light sensitive molecular system. It's like a gas system, and then you study the response on the picosecond and femtosecond time scale. And so the reason why you would do that at CXI is that you really need the UHV, in order to get the background signal very, very low. So any type of gas scattering, background like scattering really dilutes this signal, and the signal is again from a gas, so this is very, very, very weak. I just want to mention briefly here though, so the science that is described here is actually these randomly oriented gas phase molecules. There's another type of gas phase chemistry that you can do where you actually use a laser pulse to align the molecules before you pump them. And so that is another type of gas phase chemistry that one also does. But the one that we've been doing most recently is kind of these randomly oriented like gas phase molecules. And so you can imagine, because it is randomly like oriented, the data analysis is quite complicated. And so if you're all interested in that, I would recommend that you look at this paper or talk to Mike about the details on that. So that is it for me. Maybe we can go to Mike and he can show us some of, so I will stop my sharing the screen.
Right.
Perfect.
So yes, this is CXI. This is the control room. As you see, relatively empty.
Matt's here, of course.
Oh, okay, Matt is there. Hi, Matt.
Yes, hello.
Oh,
there he is. He's busy.
Okay.
He's always busy.
Yeah. So this is.
Let's start up beam here.
Sure. That's a good idea. So this big. Okay. So this big white box here actually contains the 1 micron KB mirrors. So that's there. This is for temperature stability. Unfortunately, maybe we can move on to the next one where, well, that's just a big screen. Okay, that chamber right there, that's the nanofocus KB mirrors. So yeah, so the picture that I showed you of the KB mirrors is that with this big metallic tank off. Yeah, you can't see it. It's anyway, they're 2 very shiny pieces of silicon, which are polished very precisely by JTech. And so if we move on, so this kind of empty space here is where the nanofocus would typically sit, but it's not there right now because we are working in the 1 micron focus environment. So that kind of empty tube right there is where the nanofocus and the detector that goes with it would typically sit. And then there's some diagnostics here. Yeah, diagnostics, some slits, lots of slits in order to clean up our beam. And then, yeah, so there's, yeah, the laser in coupling comes from here that you can see in the, oh yes, this is, yeah, so this
the
here.
Critical part to your experiments here, Meg.
Yes, So this is what you see here, all these optics here, is that we're upgrading our laser capabilities. So we will provide short pulse UV laser capabilities to do gas phase experiments on a wider variety of gas molecules. And so this right here, the little face, this is our 1 micron sample environment. It's typically, you know, under vacuum, probably not right now, but, and this is where a lot of the experiments happen. Oh, yes. Open it better. So it's a little bit sparse right now, but typically there's a lot of stuff in there. So the thing that comes from the top is actually a liquid jet. So the liquid jet experiments that both Tim and Ray talked about utilize that kind of a jet. And then in there you can put lots and lots of other things. We can put detectors, spectrometers, all different types of diagnostics inside like the chamber. And so if we move on, after this very nice chamber is this big empty spot where typically the detector would sit. So the detector, as I said, we're upgrading to a Jungfrau detector. Mike, if you go back to around where DSB is, that's the big detector tank with the brand new Jungfrau in it. Yes, so that is,
All right.
yeah, the one that's sitting there. Okay, anyway, that big detector tank that you saw a little bit upstream where all the diagnostics are, that's the new Jungfrau light detector. This is the old CS pad detector that sits behind the serial sample chamber, which is that other face. So, yep, that's CXI.
All right.
Great. Thank you so much, Meng. So far, I don't see any questions, but maybe as the other presenters, if you have time to stay on a little bit longer, maybe there will be some more questions. Sure. Thank you so much. And then I will hand over to Hedja.
Hello. Okay, I share my screen. Okay, can you hear me?
Yes, and I can see your slides.
Thank you so much. So hello, good afternoon. I'm Hedja Lee, MEC instrument scientist. In this slide, I'm gonna give you a brief presentation about MEC and the stations with 2 examples of science case and experimental capabilities. So where do we find such extreme conditions in nature and why are we interested in them? Here, left figure shows schematically the region of the temperature and the density plane where measuring extreme conditions are important. The region broadly indicated by orange color and red color have characteristics of the solid and the near solid density, which has an analog to pressure, typically tens of GPa to a few of TPa, and temperatures ranging from the 1000 Kelvin to the higher than this 1 million Kelvins. The status of the Earth core or inside the Earth or structure of large planets such as Jupiter, brown dwarf, or Sun, and the planetary impact phenomena corresponds to this regime. Theoretically, the plasma in this phase diagram in this regime can no longer be considered a thermal bath like a classical plasma, and the atoms are no longer well described by their isolated atom behavior. So it provides a tremendous challenges to researchers. We have put a lot of efforts to create and understand this regime through the studies of high energy density physics, warm dense matter, high pressure physics, geoscience, planetary physics, lab astrophysics, relativistic laser plasma, and fusion research. Experimentally, MEC offers a possibility of exploring these new frontiers in this area to users. I would like to show you 2 examples of science case studied at MEC. So one is a study on phase diagram and kinetics of phase transitions. The PI, Ariana Gleason, and her group studied fused silica with shock compression. This is an example of the snapshots of diffraction raw data. Under ambient conditions, ambient pressure, it shows amorphous phases. As shock wave propagate into the fused silica, then the amorphous phase transitions into fine-grained crystalline stishovite high-pressure phase with the time delay. Through these changes, she and her group could study the phase transition kinetics to stishovite during compression, and from this stishovite high-pressure phase to low-pressure phase on shock release. Another example is a study on the relativistic plasma dynamics measured in real time. The small angle X-ray scattering SAX technique was implemented at MEC to measure the fast plasma dynamics of solid driven by the MEC choppers lasers. The PI, Thomas Kluger, and his group studied and measured the expansion of the solid target grading surface. Here on oscillatory, this behavior of the expansion parameter was identified as an evidence for plasma jets periodically superimposing and dominating the signal. This was directly measured, observed in a single shot, and the results with time delays are the first direct verification of simulations of the plasma density evolution with relativistically intense laser irradiations. So, MEC instrument is located at the Phi experiment hall next to the CXI. The inside hutch, MEC equips a big target chamber of 2-meter diameter and combines the sub-micron focusable hard X-ray beamline covering 5 kb to 25 kb. Sorry. With high power and high energy optical laser systems. This photo shows the in-target chamber. The spacious and versatile target chamber accommodates several diagnostics around the sample and the relay optics for in-air diagnostics and the beam delivery optics. Dedicated in-house diagnostics of this visor, X-ray diffraction detector, X-ray Thomson scattering spectrometer, and XUV and emission spectrometer and X-ray imaging diagnostics are available for users. The nanosecond long pulse laser system is used as a shock drive, reaching high pressure regime. So about 60 joule for 10 nanosecond square pulse is delivered in 2 beam passes. For super Gaussian pulse profile, we use continuous phase plates in a spot size of 150 micron, 300 micron, or 600 microns in diameter. Pulse shaping of this square shape pulse or ramp pulse or step pulse are available. And then also change of pulse duration between 5 to 35 nanoseconds are available for specific users' experimental conditions. We provide standard configuration experimental setup for shock compression study. Here, these long pulse, nanosecond long pulse lasers are delivered through this fixed optics, through these 2 beam passes, and the X-ray beam is normal instance to the surface of the sample. X-ray diffraction diagnostics, EPIX 10K quads captures the diffracted X-ray beam from the target in an angle of the 8 to 70 degree in 2 theta. The right plot shows the Q range coverage by these 4 detectors depending on the X-ray photon energies. For example, if we use 15 keV X-ray photon energy, that case the structure factor over Q range of the 1.06 to 8.72 will be measured. While if we use 11 keV X-ray beam covers smaller range of the Q coverage. So higher X-ray photon energy delivered by LCLS-II will allow us to reach higher and wider Q range measurement. This is a table of the short pulse laser overview. 45 femtosecond or 130 picosecond pulse duration will be available at 800 nanometer. And the pulse energy is 1 joule for compressed beam and 1.5 joule for uncompressed beams. We provide F6 OAP focusing optics, providing higher than 10 to 19 watt per square centimeter intensities. X-ray synchronization will be better than 100 femtosecond RMS shot-to-shot jitter and measurable with time tool with the less than 10 femtosecond accuracy. For experiments using these short pulse laser systems, we allow users to design experimental setup around our standard beam delivery configurations like this. We provide this short pulse laser beam delivery with F6 OAP focusing optics. We recommend to this target angle set to this 35 or higher angle to reduce the back reflection. In this cartoon, this green area is open for users diagnostics, and that allows users to set this some other equip the other diagnostics. Of course, users want any other experiment setups beyond these standard configurations. Layouts are available for specific experiments. In summary, the MEC provides the combination of hard X-ray LCLS beam and high power and high energy optical laser systems, allowing us to study matter in extreme conditions. And the MEC is moving forward with the substantially upgrade the high power laser co-located with the LCLS hard X-ray beam with high energy shock drive and petawatt class high CPA lasers. Thank you so much. Any questions?
Thank you, Haja. Thanks very much for this overview. If you can stop sharing your screen.
Yes.
We might be able to see something from Mike. Mike, are you still on? Yes, there he is.
Yes.
Hello.
Oh.
Yes. Yes. So here, this is the MEC hut, as I showed as a cartoon. Here that the black box is that enclosure equip this secure this optical laser systems, and then this optical the visor diagnostics inside this black big enclosures. And then the chamber is here. Mike, could you open the door?
Let's see. Let's hope Oliver doesn't get mad at me.
Okay, see, now you see a lot of optics. So actually X-ray beam comes from this right side, and then there is already a platform for the standard beam configuration delivery for the shock compression. And this the in front of that, could you look at, yes, stop there. This is the, in addition to this standard configuration for high shock compression, and then we tailored the terahertz setup what users brought. So this is the additional terahertz diagnostics in addition to this our long pulse laser high pressure setup case. This is we are almost ready for the experiments in run 18, and then waiting for the final touch with the starting. So the chamber is quite big, so we ask users, actually we have the about minimum 3 days or longest up to 3 weeks of setup time with users, depending on the complexity of the experiments. Yep, so actually all the doors you can open, or here you can open, could you, oh yeah, okay. Could you show this? Okay, left side is the enclosure. Don't open it. I mean that is it what's the class? Could you put this door side?
No, laser's off.
Laser off. Okay, then you can open it.
Yeah.
Okay. Usually we lock this enclosure. That case is class 1, but when laser is on, when you open this enclosure, then suddenly it becomes class 4 status. And then under such emergency, all the laser shut down. But now it's laser off status. Okay, this is the part of the nanosecond long pulse laser. And then could you look at a little bit right side? Yes, that's from this enclosure. Hearing this optical system, there's a pipe. This is not the Bay Bridge, I'm sorry, but this is the beam transport nanosecond laser. Here, our optical laser is quite high and high energy. So beam size is about 50 millimeter each beam. So quite big, kind of big ones. So that's why it looks like quite very big transport. And here you see another beam transport in vacuum. The other one was for the nanosecond long pulse laser in air, but this is the beam delivery transport for the short pulse laser for 25 terawatt. So that goes to the inside the chamber. Could you open that one, that door? Thank you so much. So yes, could you look at this right side? Yeah. You see that the orange paper at the left, that's something kind of we blocked. We blocked the beam here. Also, sure, there is a gate valves, so always it's safe. But is that this once in class 4, when you do the experiment, first we set this remote controllable iris is there, and then through the beam, we also control the beam path over this, make sure the beam positions. This experiment is designed for using this long pulse laser and the terahertz beam. For the terahertz beam, we also delivers this short pulse lasers. This is very kind of X-ray beam, nanosecond laser, and then also femtosecond beams will be there. All three be there together. Very challenging for the temporal overlap and then all the synchronizations at one spot. Okay, and then at the end, behind the chamber, could you look at? Now we don't have look at this behind the back of the chamber. Yes, actually right now we are missing the beam pipe flight tube. And then we connect this flight tube behind this chamber to the wall side. Could you turn right side more and more? Yes. Yes. So there, just in front of this beam block of the water bank, we set this imaging diagnostics. So we have the distance from the target to this detector, imaging detector, is about 4 meters. So through 4 meter distance, we gain the more magnification in addition to the microscope objective. So we could maximize that this spatially and then spatial resolution, we can get the gain of the spatial resolution. So we use such a diagnostics for the phase contrast imaging and then other radiography experiment. Yep, we have also some island of the optical tables. When users bring their in-air diagnostics like interferometry, and then we set up there. In principle, we keep the hutch keep clean. So usually we wear lab coat, hairnet, and then the gloves, and then the shoe covers, all those together. Well, not super clean, but dust-free areas for this high energy and high power optics.
Right.
Yep.
Great.
Thank you so much.
Thank you so much, Hedja. This was really nice. Could you also have a look at the Q&A and maybe answer some of the questions in writing?
Yep.
That would be awesome. Thank you so much. And then we have our last speaker of this long tour, and that is Jie Yang. Unfortunately, we can't give any live stream from what he's going to talk about, because he's talking about mega electron volt ultrafast electron diffraction. That is not directly, at least not spatially related to LCLS, but is now also part of LCLS, and it's a user facility where you can apply for beam time. Jie, please take the stage.
Thomas, I thanks. I was since we can't really show the audience a tour on this, I'll get going. I'll disconnect off this this webinar for you.
Okay, thank you so much, Mike. That was
you guys
really.
have a great time.
You too. Thank you.
All right. Bye-bye.
Bye-bye.
All right. Thanks, Thomas, for the opportunity. And everything looks fine on my side, the slides?
Yes, and I can hear you.
All right, great. So I'll give a brief introduction on the instrument of MEV-UED. So we became basically we joined the LCLS family last year, and now we are basically under the LCLS instruments. We're one of the LCLS instruments, although it's in a separate location, a separate beamline, but now we're one big family. And MEV-UED stands for mega electron volt ultrafast electron diffraction. So a brief history about SLAC MEV-UED. So we started basically in response to this DOE workshop in 2014 on future electron scattering and diffraction. That's when we started the initiative at SLAC, basically with this goal to provide world's leading ultrafast electron scattering instrument. And of course, we started with a solid phase run in 2014, and in 2015 we demonstrated the first gas phase run. And between 2016 and 2018, we are basically switching between solid and gas phase for 3 times and did a lot of nice experiments back then. We also demonstrated the first warm dense matter run. And in 2019, which is last year, we demonstrated another new capability, which is a liquid phase experiment. We also joined LCLS that year and had our first official user run, which is focused on the solid phase samples. And 2020, basically right before the shutdown because of the COVID-19, we are in the first official gas phase user run, which is the second official user run, but first for gas phase. So what can UED study? Basically, we heard a lot of different capabilities for X-rays and free electron lasers. So there are very diverse capability from the X-ray side. For the UED, it's pretty simple and focused. So we basically study the structural change of sample, which can be molecules or materials, etc., by probing the time result diffraction pattern. So here there's hope this animation works. Not sure, okay. Some technical difficulties, but the idea is basically we'll do a pump probe experiment, and by tracing the change of the diffraction pattern, we can basically figure out the change of the molecular structure in the real space. Therefore makes the so-called molecular movies. So here I give a quick introduction on the difference between X-rays and electron diffraction. Of course, we heard X-ray can also do diffraction with hard X-rays. And there are a couple of differences here. First, mostly they basically, in principle, they provide very similar information, basically what's the real space structure of your sample is doing after the photoexcitation. But here I list a couple of differences. First is Q range, where currently electron provide up to 12 inverse angstroms, while X-ray now it provides up to 4. But we also heard that with the upcoming upgrade that can provide 25 keV X-rays, that this basically the two will be very comparable. So this is more like a technical difference rather than a fundamental difference. But the next two are from the physics. Basically, they're the fundamental difference. So electron scatters from both nuclei and electrons. So it's basically Rutherford scattering, or it basically scatters from all the charged particles. That includes the nucleus. Well, X-ray scatters from electron clouds. So that's Thomson scattering. So these two are different. I mean, for most atoms, they are comparable because you always have a lot of core electrons around the nuclei. But for some light atoms like hydrogen, the case will be quite different. And the third is the inelastic components. So they actually have the same information, but for electron, for small angle is dominated by inelastic, while for X-ray, small angle is dominated by elastic. So this is also a very neat difference that the two techniques have different strengths and are basically more suitable for some specific scientific questions. And of course, the last difference is the electron diffraction is about 100 times cheaper than FELs. So here is a engineering drawing on the top where we basically start with a radio frequency gun. This is actually the backup gun, so exactly the same replica of the LCLS electron gun. But the difference is we basically do not send it to any more accelerator, just takes the electron from the gun and send it through a couple of diagnostics and some differential Palming section directly to our sample. So it's basically the simplest accelerator you can imagine. And the bottom, it's the picture in the lab where the whole thing actually is within 5 meters. So it's very compact compared to a free electron laser. So the performance can be measured by a set of resolutions. So the first, of course, I mentioned the Q range is about 12 inverse angstrom, and of course the Q space and the real space are connected by a Fourier transform. So the higher Q range, the better your real space resolution is. So if you want to get a spatial resolution from this, you can do a simple relation 2 pi over Q max. It give you a 0.5 angstrom for its half max. But this is basically tells you how basically the width of your peak in the real space. But if you want to figure out the center, which is basically typically if you want to extract structure, you do some fitting, and you can get a much better precision than the spatial resolution, and that's we demonstrate on the order of 0.01 angstrom and 1 degree in bond angle. And the Q space resolution is about 0.17 inverse angstrom, and this is something that's far worse than X-ray that we are also working on to improve. And the final one is a temporal resolution. Now we have about 150 femtosecond for its half max. That's also about a factor of 2 worse than the typical performance of LCLS, sometimes even more. But also there are ways to improve, but this is just what currently we can do. And there are some more parameter lists in these two tables. So the top lists the electron parameter, so we can operate from single shot all the way up to 360 hertz at the moment. And we are also we have planned to upgrade to a kilohertz next year. Beam energy is typically 2 to 4 MeV, and the electron bunch is typically 10 to 4th. If you want the best time resolution, and also if you want to sacrifice time resolution, you can get more. Coherence length is about a couple nanometer, and this is something that we also are working on when we're targeting, for example, bio samples. And the beam size are typically on the order of a couple hundred microns. For the pump laser, now we have quite a lot of capabilities. We can do basically the fundamental of Type Sapphire 800 and also the harmonics up to the 4th harmonic. We have also an OPA and the UV extension section that give you tunable from 240 nanometer down to about 2.4 micron, continuously tunable. We can also do mid-IR and terahertz with some help from the LCLS laser group that we also have demonstrated experiments on. So although our capability is basically focused on probe the time-dependent diffraction pattern, but the variation came from the sample environment. So we can do solid phase samples, warm dense matter, gas, and liquid phase. So I will go into each category and give a brief introduction on each case. So first, the solid state sample is the science we start with, and it's relatively straightforward. So basically, you put in a thin sample. It needs to be thinner than 100 nanometer to avoid multi-scattering. The sample can be cooled down to 30 Kelvin, and we provide a 6-dimensional sample stage. So basically, you have 3-dimensional translation and 3-dimensional rotation that you can look at different angles of your diffraction pattern. And we also provide a microfocusing option. So our beam is comparably larger than X-rays, for example, with typically a few tenths of microns. And now we demonstrate down to like 5 micron level, which helps you to extract local information of your sample. And for warm dense matter, it's also the solid phase sample, but the difference is basically we excite the sample into the warm dense matter region with a very powerful laser. That means you basically damage your sample in a single shot. And in this way, what you're studying is an irreversible process. So you cannot do like a typical pump probe, like you did for solid sample, that you just keep pumping and probing the same sample over and over again. So here what we do is basically we have a lot of samples, like hundreds of samples, and we basically take a single shot at different pump probe delay and basically combine them together later to form a complete movie of what happens to the sample, as demonstrated in this case. And the liquid phase is what we basically demonstrated quite recently last year. And the paper, if you're interested, the machine paper is published earlier this year here. So the brief idea is basically for electron diffraction to work, you need a very thin sample, 100 nanometer or less typically. So we use basically this liquid sheet technique that you heard in a couple of previous talks. Basically, it's based on this chip where you have one liquid channel and 2 gas channel to kind of blow on it and flatten it. So we demonstrated both static in water and also a couple of other solutions. Also, we demonstrated a pump probe diffraction also works with about 200 femtosecond time resolution in this case. Finally, gas phase. Gas phase is my background, so it's also a rather simple idea where you dump your gas sample into the interaction region with a nozzle. It could be a continuous or pulse nozzle, and you basically do a pump probe with this fairly simple geometry. But to make the experiment work, of course, we need to introduce a cold trap to kind of make sure your sample does not ruin your pumps. And also we need to separately introduce the incoupling mirror. So they need to be differentially pumped. Otherwise, they will basically degrade pretty fast. And for the sample to work, it needs to have high vapor pressure. It needs to be low thermal decomposition. So basically, it can be heated, and prefer to have large structure change, heavy atom, and the time scale basically fits the time resolution of our instrument, which is longer than 150 femtosecond. Okay, so here I give 2 brief science cases to just to show you kind of give you an idea of what we typically can do. So this is the paper from Arlene group published last year, where they were able to observe basically a topologic switch in tungsten dielectric material. Basically, what they saw is after the photoexcitation, they kind of are able to excite this shearing motion in a 2D material between layers. That's very, very nicely captured. And here for gas phase, this is a paper just published a couple of weeks ago that we show basically that we are able to resolve both nuclear and electronic dynamics from a diffraction. And the trick is basically the inelastic scattering from electron are focused on small angles, and that part actually encodes a separate dynamics. So that's a very neat thing to reflect from a single experimental data set. And here, I'll just leave a couple of pictures of our staff and users working on different projects at different time. And thank you for your attention.
Thank you very much, Jir. That was great. And sorry that we couldn't give you any live footage. There are a few. There's so far one question for you on the chat, and this is actually, I think, an important question. Mm-hmm. What is the number density of gas phase molecules needed to do UED?
So number densities, we typically need to be pretty high, 10 to 15 per cubic centimeter level, 10 to 15, 10 to 16. If you have heavy atoms, it might be relaxed a little bit, but not too much. So this is a ballpark.
Okay. So far, there are no more questions for any of the participants who is interested in writing a UED proposal, which is completely possible. If you're interested in gas phase chemical dynamics, Jir will join this group, and you will be able to form a subgroup. If you are more interested in solid state dynamics, you should maybe contact Jir directly. That is also a possibility. And there is another question. What concentration of the photochemical solute should be high enough in a liquid jet?
So for the solute, we tried a couple of experiments in last round, and now it's pretty limited. So basically, you need 100 of or 50 to 100 millimolar of concentration with heavy atoms inside. So it's pretty tough still, but we believe with a kilohertz upgrade, we should be able to do better with lower concentrations.
All right, that's all the questions I see. Maybe people are also a little bit fatigued now. This was unfortunately a long session, but the logistics required it to be all done in one session. So I want to thank all the active participants here, the speakers, once more. This was really great, and I really appreciate, and I'm sure the participants also appreciate that you made time for this. Yeah, that's really great. And with that, I would like to close the session. The participants should now start to meet up with the proposal mentors. I'm hoping this is all working out well. If not, we'll try to fix it, and I apologize in advance. We will try to figure this out with the mentors over the Slack channel and with the proposal group members over the Canvas platform. Shito, did you want to mention anything?
No, I think we're good. There seems to be, thanks to all the speakers, of course. Thank you, everybody. I think we're doing fine. And if anybody needs help, then they can, yes, Slack channel or email if they're having a problem.
Perfect.
Yep. All right.
Okay, then I will close the session, and I will see everybody again tomorrow for the second lecture of the summer school. Thank you, everybody, and see you tomorrow.
Thank you, Thomas.
Thank you, Jir.